Hi, I'm Lawrence Krauss, and welcome to the Origins Podcast. This episode is with the theoretical physicist and cosmologist Alan Guth, the father of inflation. In 1979, Alan, then a postdoc, had a sudden realization that changed the world of physics and changed our understanding of the universe. He produced what is now the standard picture of what we think happened in the early universe in order to explain the properties of the universe we see today. It produced a sea change in cosmology and gave us a model that allowed predictions to be made, which are compared with observations very favorably, as we discuss. But the interesting thing is, Alan actually had that realization when he was on what would call a terminal postdoc. Like many young postdocs, he was bouncing around the country and was on potentially his last postdoc when he had that realization that changed his life and, as I say, changed physics for the better. Alan is a remarkably coherent, deep-thinking, clear speaker, and I've always learned a lot from speaking to him. We talked about his own experiences in physics, what got him interested in physics, and his experience of discovering inflation, but we went beyond that to talk about the physics of the universe itself, from the beginning of time to the end, whether there is a beginning of time, whether there is an end to the universe, multiverses, and of course, contrasting inflation with other ideas, including some that have been proposed by Roger Penrose, which Roger and I talked about in an early podcast. I hope you'll find it enlightening. As I say, I always find my discussions with Alan enlightening. He's been a colleague, a collaborator, and before that, a professor of mine. And it was a real pleasure to bring him on the podcast. I hope you enjoy it regardless of the platform on which you watch it, whether you watch the YouTube version or whether you watch the ad-free version on our Critical Mass Substack site. And no matter how you watch it, I hope you'll subscribe to the appropriate platform, our YouTube channel or Critical Mass. The ad-free version, the video ad-free version, requires a paid subscription to the Substack site, and that money goes to support the Origins Project Foundation, which makes the podcast possible. So I hope you'll consider supporting it as well. In any case, no matter how you watch it or listen to it, I hope you find it enjoyable and enlightening. Take care. Well, Alan, it is a true delight to see you again. It's been a while, but thanks so much for agreeing to be on the podcast.
Great to see you.
Yes, we've gone back a long way together, in fact, right back to when I was in graduate school.
Oh, yeah, I remember.
Where you played a role, for better or worse, in allowing me to have a PhD. So,
Oh.
yeah.
I guess that was for better or for worse. Well, we'll see.
Yeah, that's right. There's still time. There's still time. Exactly. The jury's still out. There's still time. And one of the things I like about doing this is that I can learn things about people I know well that I didn't know about them before. So, because I try and do a lot of research, and I was intrigued actually because so some things about your background that reminded me of my own in a way, but I don't know if it's true. So you grew up in New Jersey. I was born in New York, but you grew up in New Jersey, and your parents had a grocery store and dry cleaning business. Is that right?
That's right.
So did either of them go to university?
I think my father went to the junior college for a couple of years. My mother did not go to university at all.
Okay, she was a homemaker primarily, or did she work in the business? Okay, she was a homemaker.
Well, she's primarily a homemaker, but she did help out in the store.
Yeah, sure. Now, because my parents owned a little store, and neither of them went to university, as it turned out. But I'm always intrigued then to find out what motivates people to go become educated and also go become a physicist. Now, you were a nice young Jewish boy in New Jersey. Your mother wanted to be a doctor, maybe, or no?
I think they wanted me to be an engineer.
Oh, engineer. Okay, well, that's good. That's which, did they influence you, or were they influenced by it? What got you interested in science or math at the beginning? What was it?
Yeah, a little hard to know for sure. It did not come directly from my parents. My parents certainly expected me and my two siblings, my two sisters, to go to college. That was kind of a foregone conclusion
Yeah.
in our community, even though the parents had not.
Yeah, that was
More
children do better.
opportunities, and
Yeah, yeah.
it was definitely what was expected. As far as science versus other possibilities, I certainly know that at a very young age I was interested in science, and I remember what I thought was a marvelous TV program called Watch Mr. Wizard.
Oh, I
I
love
don't know
Mr.
if
Wizard.
you can remember that or
Oh
not.
yeah, I love Mr. Wizard.
But I think he did continue for quite a while. So you probably got to see some of them as well.
Yeah.
Don Herbert is the
Yeah.
name of the person who created it. And I thought that was marvelous. And maybe that's what hooked me on science. I don't know. Then I started reading some books. I didn't have a large number of books. I remember particularly a book called The Universe and Dr. Einstein, I think by Lincoln Barnett. And I know that book got me very excited about science.
Did you ever read any of those books by Asimov or Gamow or any of those things, or when you were younger? No.
I don't think I read Asimov. I probably did read 1, 2, 3 Infinity by Gamow, and
Yeah.
was also very impressed by that.
Yeah, no, those books and others by books primarily by physicists were I think part of what got me interested in physics. There was a long road, but you knew, but you had an early aptitude for mathematics. How did you know that? Just be doing well in school, or were there other things?
Well, I did well in school, but I remember I was also learning some things on my own. I remember I learned how to calculate square roots long before we learned it in school, and felt very proud of myself that I knew how to calculate a square root. I think I learned it from some book. I forget how I acquired that book or what book it was.
Well, okay, so did you have good teachers in school that encouraged you to do science, or one way or another, or were they influential at all, or were you mostly self-motivated?
Right. I guess I somehow don't remember very well my elementary and 7th and 8th grade teachers. I don't think they had a strong influence on me. I did have a physics teacher in high school who I thought was great. By that time, I think I already had decided I wanted to go into physics. So I'm not sure that he turned the course of the tide,
Sure.
But he certainly got me very enthusiastic about it. It was a kind of strange situation. He didn't actually know that much physics, but he had the personality that was incredibly exuberant. He was incredibly excited about different things about physics, and it was contagious.
Well, I think that, yeah. No, I think that's important. I think that enthusiasm is more important in some sense than knowledge in teachers, especially if teachers are willing to say, I don't know, when you ask the questions, and say, hey, maybe we can figure this out together. Or I think that's the best thing a teacher can do. There's no need for them to be encyclopedic at the high school level. It just, hey, this is interesting and we can work out together, and I find it fascinating and I'd like to learn more, and that sort of thing. I often say teaching is selling in some sense, but certainly at the high school level, I think it is. It could be.
Yeah. I agree, and that is the kind of person this teacher was.
Now, I was going to ask you where you I knew you went into physics at MIT, but you say you already decided to do physics in high school. Did you ever think of doing mathematics or no, or was it always?
Somehow I think it was always physics. I was, of course, interested in mathematics, as any theoretical physicist is, and enjoyed it. But I guess I always thought it was much more meaningful if it was directed at understanding nature.
Yeah, sure.
Than just pursuing abstract axioms.
Well, something I can't disagree with, but since we're both theoretical physicists, it's not surprising. I did a degree in math as well as physics, but it was so I wasn't certain. But you knew you wanted to go into physics, and you actually, something is interesting to me. You attended several different high schools. Is that true? And why? That's what a biography of you says somewhere, and I want to know if it's true.
Yeah, no, it's not true.
Oh,
So I don't have
Okay.
to explain why.
Okay, good. You were, I know,
Uh,
the way you looked, I thought, why? I thought there might be a neat story there, but
yeah, no,
the
the
neat
only
story
story
is it's a
concerns the author of the article.
okay. Well, that's good,
So
but
I grew
nevertheless,
up in a town called Highland Park. I
hmm
went to Highland Park public schools throughout,
and they were
and
good.
I left high school after 3 years.
Yeah, well, I wouldn't get that. That I knew was true. And you
That is
left.
true.
Now you left. Interestingly, you left. Um, well, went into a program in IT that allowed you to do a bachelor's and master's degree in 5 years, but you also left because of concerns about the Vietnam War. Is that true?
That's not relevant for high school, but it is relevant to the 5-year program at MIT.
Okay, so why did you leave high school after 3 years?
Mainly just the science teachers wanted me to leave.
You weren't poorly
Wanted me
behaved or
to-
anything.
I was pretty well behaved, I
You've
thought.
always been very well behaved since the minute I met you, so I can't imagine that you were.
But actually, it was the science teacher, the chemistry teacher, who I would have had the following year, who suggested that I leave high school and go on to college. And I guess maybe he first talked it over with people in the guidance department, and everybody seemed to think it was a good idea. And then they talked to me, and I thought it was a good idea.
Now,
And this was in the spring of my junior year. It was after all of the applications for colleges we do. But they asked me where I wanted to go, and I said MIT. I didn't know a lot about colleges at that point, of course, but my sister had gone to, my sister was 3 years older than me, was a student at Lesley College in Boston,
oh.
and she was dating MIT guys. And I got to meet some of them and came to be impressed that MIT was the school if you wanted to do science. So I told my guidance counselor in high school that I'd like to go to MIT, and he called MIT, and they arranged it.
Wow, it's a different world back then. I was going to ask
Yeah.
about. It wasn't normal. It wasn't a standard procedure to leave before your last year. It wasn't as if the MIT had an official program for anything like that.
No, I just came into MIT as a normal freshman, as far as MIT
Okay.
was, as far as
But
the way
you
they
did,
treated
you,
me.
and you found yourself as prepared as the other freshmen, I guess, or you didn't have to do any remedial work.
Yeah, I did. I was surprised. I expected to be outclassed by everybody. I also joined the track team. I was tremendously outclassed there.
Okay.
I was the best broad jumper in my high school, but
And then-
at MIT, there was a freshman who could jump about 2 feet further than me.
You see, well, I figured if you want to do sports and you want to excel, MIT would be the place to go. I would have thought.
You would have thought, right? Well, it depends what level you're at.
Yeah.
But they're pretty
I would-
spectacular people in all fields at MIT. So I also
Well,
at MIT, I was the best chess player in my high school. So I went to the MIT chess club one day and got wiped off the board by somebody who was playing 4 of us blindfolded or something like that. Again, it was just a totally different class.
it is.
But it still turned out in physics and in math, I was doing
Doing well. Yeah,
having
and
near the top of the class.
yeah, okay, and so you didn't have to take any math. You'd done enough of the calculus and everything in high school to
Yeah.
do that. Yeah, no, it's okay, and physics. So I was going to ask. So MIT, like the decisions most people make, my experience for going to university usually are poorly informed ones.
Mhm.
You get you visit for a day and it's a sunny day at that day at university or something like that. But it was in this case it was Boston and MIT students. So you didn't think of the other. So you really never thought of any of the other places, any of the Harvard or Princeton or any of that stuff. The Princeton was closer to home, certainly.
Yeah, right. No, I never thought of Princeton. Never thought of Harvard really either. I do, however, recall that that I knew a student who was a freshman at Harvard, and when I went to visit MIT, I stayed with him at Harvard and visited MIT during the day, and the visit reinforced my belief that MIT was the place to go.
It's interesting. And I remember when I got it. Of course, I went to MIT. Well, you went to MIT as a PhD student as well, but I moved from a small place in Canada to go do my PhD at MIT, and I remember visiting and staying with a friend of mine, a physicist who uh, was at Harvard, and I went down the road to MIT, and I just kind of immediately felt like it was. Yeah, it was. There was. I liked the atmosphere there. As you know, I
Yeah.
later went to Harvard, but I've always liked the sort of no nonsense attitude of MIT, and the fact that they didn't have a football team, which wasn't that influential in my decision. But
Right. It's no
uh,
longer the case, I think.
so you wanted to do physics, and you weren't turned. And during your undergraduate career, that was only reinforced. You never thought of doing anything else.
That's right. That is right.
And you did something which again is not so skipping last year of high school is unusual. The other thing in your career that's somewhat unusual is staying on to do a PhD in your institution. A lot of institutions encourage, and I used to encourage my students to go somewhere else.
Right. MIT generally does too.
But you couldn't be discouraged. Is that you were
Right,
comfortable
right.
there? What was your reason? You were just
Well,
comfortable there?
here the Vietnam War did play a role.
Okay.
By the year that I would have graduated, the year that I would have gotten my bachelor's if I got my bachelor's in 4 years, was precisely the year when graduate students were no longer deferred from the draft. So MIT actually did quite a bit to try to help its students do as well as possible to stay out of the draft. And one of the things that they made possible was actually this 5-year program was created at that point.
For that reason.
For that reason, well, not officially.
I wonder.
But yes, for that reason.
Well,
so I was able to officially remain an undergraduate for another year.
Okay.
And that would only have been possible by staying at MIT.
I see. But then you could have after master's gone to do a PhD elsewhere though. But
perhaps. Actually, though, then there was another draft-related reason to stay at MIT, which is that while graduate students were no longer deferred from the draft, MIT created something called a full-time teaching assistantship, which involved more teaching than a standard teaching assistantship. And they convinced the Massachusetts Draft Board that this was a critical occupation that was worthy of a deferment. So that's what I did the next year.
I love him. Another reason I like MIT some recently I've had issues, but yeah, no, that's great. I wonder if, my friend Noam Chomsky, who was at MIT and very strongly anti-war, had any role in encouraging them to do anything. But it's great that they did that. I remember when I was there, it was a different thing. What they did when I was there was accept an incredible number of Iranian students, because of the revolution that was happening in Iran, and they took a lot of students in who wanted to continue their education. So let's applaud them. That's great. You're the interesting thing, you're not that you're about 6 or 7 years older than me, 7 years maybe. Yeah, 7 years older than me. And the interesting thing to me about when I began to think about the early stages of your career was that you were interested in particle physics, as was I. We both trained as particle physicists. But that was a kind of a weird time in particle physics. It was kind of I wouldn't say a lull, but it was a time. I mean, there was an explosion in the 1970s in many ways, and you were part of it in a key way later on. But the 60s were this time of uncertainty and a lot of confusion in the field. And even though a lot of the key ideas were developed in the 1960s, that later became part of the standard model of particle physics, it wasn't that clear in the early 1970s, and certainly when you began your PhD, and even when you ended your PhD, that the standard model was that things were settled with a beautiful theory. That things were still very confused. So why did you focus on particle physics, and where were your interests at that time?
Right. Well, I agree with your description of the field. There was the standard model in the late 60s and early 70s. It was sort of one of the models that was on the table, the model that later came to be called the standard model. But there was a lot of confusion, even whether or not field theory was the right language to describe elementary particle interactions. But I think what fascinated me about science from the beginning was the goal of understanding nature at its most fundamental level. And that is what particle physics was trying to do.
Yeah.
By the way, I described my interests as if they were kind of constant over time. I think they did sharpen over time. When I was in grade school, I think I knew I wanted to be a scientist, but I didn't really know how to tell one scientist from another.
Yeah, I know.
And probably it was high school I decided I wanted to go into physics, and probably it was while I was an undergrad that I decided I wanted to go into theoretical physics and theoretical particle physics, I guess.
Any professors at MIT that were influenced? Steve Weinberg was there then, wasn't he? Was he at MIT then, or
he was, yeah. In my later years as an undergraduate, while I was a graduate student at MIT, yes, and I took general relativity from him while he was writing his famous book.
Yeah, that's great.
And I was incredibly impressed by Steve Weinberg. And he certainly had a strong influence on my thinking.
Yeah, no, and me too. And an amazing physicist, a great loss for humanity when he died recently.
Yes.
But and I know, and interestingly, a number of the areas of research that you pursued related in one way or another to things that Steve had been thinking about. And I don't want to jump ahead too far, but of course, in some sense, the movement of particle physicists into cosmology, which wasn't really kosher early on, something that he kind of also heralded. And I'm wondering if well, let me ask, it's going ahead of things, but with general relativity, of course, like everything that Steve did when he wrote a book on it, when he taught a course, he would write a book. When he did either, he'd develop a comprehensive knowledge of things. And of course, since general relativity's testing ground was astronomy and astrophysics, I suspect that's where he began his interest in cosmology and astrophysics. Did that come across to you at the time?
Partly at the time and much more later. Steve really played a crucial role in my getting involved in what led to inflation. And maybe we'll continue the story later and get there explicitly. But while I was a graduate student, I did take, along with Steve's general relativity class, I did take a cosmology class, which was co-taught by Steve and Phil Morrison.
Oh, Phil Morrison. I was wondering if it was Phil Morrison.
Too.
Yeah, maybe two legends, Phil Morrison.
Right.
Yeah, it was amazing and a wonderful man. I used to, as a graduate student, I never took a course from him, but I used to just go into his office and talk, and it was always open. And I remember trying to emulate that later on. I mean, I just was a lowly graduate student. He said, "Come on in,"
yes, he was a wonderful, wonderful person, and
also committed to issues that were relevant at the time, and not just anti-war, but later on issues of missile, of protecting us from false claims about defense systems in the country and missile defense and other things. He wrote a variety of important books on that, and played a role. Always spoke out.
And I admired that tremendously.
Yeah, me too. Later on, in fact, my interest in the Bulletin of Atomic Scientists, in some sense, came from him as well. Anyway, who was your supervisor at MIT? Who did you do your PhD with?
Francis Lowe.
Oh, okay, great. Another great.
He was a terrific person too. I did very well.
Yeah, and he did a number of key bits of work that, one way or another, laid the basis of the Standard Model. The whole notion of what we'd call the fact that the evolution of theories depends upon scale came out of work that he'd done earlier, and led to what's called asymptotic freedom, which we may get to, because I'm intrigued. So what was your PhD on? What was your thesis?
Yeah, well, to tell you the truth, even though I was working with Francis Lowe, who has previously done this very prescient work that played an important role in developing the Standard Model, the thesis that I was doing was very anti-Standard Model and became totally obsolete by the time I finished it. I was working on the quark model, which was, of course, aimed at fundamental physics at its purest form.
Yeah.
But the version of the quark model I was working on was a pre-gauge theory model where quarks were viewed. I was just doing mesons, so I was looking at quark antiquark pairs, and the model was designed as if these were just incredibly heavy particles, so you didn't see them because they couldn't get out, very strongly bound to give an overall energy to the bound state. That was the energy of mesons.
Well, was that influence, that was the bag model at MIT active at the time? Ken Johnson and others, which was kind of a not quite a pre-gauge theory, but a standard model way of thinking about quarks in mesons. Were you influenced by that at the time or no?
I don't think that existed yet. I think that came somewhat later. If it existed, I didn't know about it at the time.
I'm intrigued when you say your thesis became irrelevant almost, because my thesis was kind of an anti-inflationary proposal for a way to solve some problems in physics, which by the time I even completed it and defended it before eminent scientists like yourself, I realized was already irrelevant because inflation was clearly correct at that point, or at least clearly a beautiful idea. I wouldn't say necessarily clearly correct, but anyway, it's interesting. At least I view a PhD thesis as I often tell my students it's an excuse to get out and do things more than something to labor over. And I'm always amazed. I always liked the fact that in physics, more so at Harvard than MIT when I was there, that at Harvard you could sort of staple 3 papers together and call it a PhD, and you wouldn't waste half a year writing a beautiful dissertation. They just wanted to get out and do things. And I've tried to encourage my students to that, but they always want to write a nice, they always want to write it all up and everything.
I see. Yeah, no, the trend at MIT now is the staple 3 papers together method.
I remember the idea was that I had to have sort of more or less 3 papers worth of work, but I still had to write a comprehensive thesis then. Now you're working on quarks and you say, as you say, anti-standard model gauge theories, which Steve helped pioneer in many ways and was a sort of one of the great scientists pushing gauge theories and as a fundamental understanding, and as they now are for at least all of the known interactions in nature. But you went. What intrigued me then? Okay, so there was this confusion because at that time, as you say, when you did your quark model, no one knew if what the theory that would then become the theory of the strong interaction was right. That people were still speculating that the whole notion of field theory was not right, and it would have to go out the window. And in Berkeley, there were all these people looking at alternatives that seemed, inventing things called string theory to try and circumvent field theory, and later on turned out to be an incorrect effort, although it was later reborn in a different form. But you went to Princeton after graduating. And I was intrigued. You were in Princeton in 71 to 74 or something like that, or probably 76.
That's right.
And of course, that was intriguingly the time that that gauge theory was used to develop a theory of the strong interaction. And you were there at that time, but if I'm not incorrect, you were not necessarily aware of it or working on different things, right?
I was definitely working on different things, and I think I was not even really aware of the development of asymptotic freedom, even though it was an unbelievably important development in particle physics that was happening right under my nose. But I was working on other things and did not notice it. I was working on things that basically were a continuation of my PhD thesis at that time still.
But okay, that's not unusual for postdocs, let's face it. I mean, you've developed a series of tools, you want to go, work on them and push them further to demonstrate your abilities, and it's not that surprising. But the career of yours that I've certainly became aware of, and that I knew later in one of your other postdocs, you really moved into gauge theories, as sort of studied the details of quantum field theory of gauge theories in your later work. When did that transition happen?
Happened pretty much when I went from Princeton to Columbia. At Columbia, while I was at Princeton, at least gauge theories were big at Princeton, but and among people who I wasn't talking to very much.
Okay.
I was working mainly with Dave Soper, who was also, I guess he was maybe assistant professor at that time, or maybe also, we started as postdocs together. I don't remember when he got promoted to assistant professor. And also Murph Goldberger.
Oh, okay.
Marvin Goldberger, after people who look up his name in the encyclopedias.
Yeah.
But everybody called him Murph.
Yeah.
M-U-R-P-H.
Another important figure at Princeton, and influencing
right.
a lot of people.
Certainly a very important figure, but also sort of towards the end of his career, so he wasn't into gauge theories. So he was happy to work with me on this, what we now view as a very old-fashioned approach to the way quarks are bound inside of hadrons.
And you moved. Look, I mean, one of the things we'll get into, and it's no secret, is that your experience was something that, coming a few years afterwards, is something I sort of expected in a way. I mean, it was really hard to get a job, and you had a career that looked ultimately like you might, not get a job, and a number of postdocs, and at each stage, however, it turned out to be very useful, because each stage you got something out of it that eventually led you to the work of inflation, which we'll get to. So Columbia, there was much more emphasis on gauge theories. Who was the people there? Was it?
I was working mainly with Norman Christ.
Yeah. Okay. Who later on did lattice gauge theories, right?
Who later on did lattice gauge theories.
That's, by the way, just so we can tell people that, the mathematics of these theories, one of which is a strong interaction, is not handleable when the interaction becomes strong. And one way to try and resolve that is to take space and make it a discrete series of lattice points and do numerical computations about things that you couldn't analytically compute. And it's become a very important area which has really led to wonderful predictions demonstrating once again that the standard model is right. But this was before his work on lattice gauge theories, I guess.
That's right. But he was very interested in gauge theories.
And the interest in sort of phase transitions in gauge theories, which I think did that come from there or later on, or was that to Cornell?
That didn't start until Cornell.
Okay, so gauge theories,
at this point, we're concerned with things like how exactly should one quantize gauge theories, which was still somewhat up in the air. And I think we developed methods that are correct, but are not the simplest methods and are not really used by anybody today. But
again, the technology of dealing with field theory was, handling difficult fundamental questions with how to handle gauge theories, which on the surface have problems because it looks like many different ways of describing them, and that's become a useful thing. But it also presents ambiguities in things like terms like of making a quantum theory. You can make different quantum versions of gauge theories that on the surface look very different, and sometimes and in general are the same. But it's kind of a fascinating feature of gauge theories.
Yeah, I agree.
And okay, so but I mean, the more technology and detailed. Then you moved after Columbia to Cornell. Is that right?
Right.
And that's where you began to make the transition. Although you were still working when you were at Cornell, the theory. So let's put this in perspective. You were 71 to 74 at Princeton, 74 to 77, I think, at Columbia, and then 77 on to almost 80 at Cornell. And the field.
Well,
what was that?
A year at SLAC.
Yeah, I was going to say 79 to 80 at SLAC, and the field, that was an amazing decade. It was because at the end of the decade it was totally different. At the beginning, everything was confused in 1970, but 1980 there was a standard model of particle physics that was not only accepted but tested and understood, and gauge theories, as we point out, had become clearly the right way to understand at least the known forces in nature. And physicists, sort of the chutzpah that came from the very heady success of particle physics to understand what was known, began to think about what was unknown, and what became clear by the mid-1970s is that there was a this standard model, which described, three of the non-gravitational forces in nature. There are only four forces: there's gravity, and the weak, the electromagnetic, and the strong force. That they could be potentially unified at a scale which was far, far away from anything we could ever measure in the laboratory directly at the time. That was an amazing leap that changed sort of ultimate sociology as well as the psychology of particle physics. This notion that one could try and extrapolate by 16 orders of magnitude to try and understand what was going on. And the fact, I guess, that it was acceptable kind of made it more acceptable to think about the kind of physics that you began to think about, right? I mean, eventually.
Oh, absolutely, yes. Yes.
And
I agree with you. Around 1980 was kind of the peak of physicist chutzpah in believing that if we can write down a beautiful theory, it has a good chance of being right.
Yeah, no, I remember going to it was a little bit, I forget when it was, but it was around then. I went to the first conference on grand unification, and it was like a prize party, everyone patting themselves on the back because they were going to make the next great discovery that was going to change the world. And because the power of what had been done was so strong that I mean, physicists were obnoxious enough at the time, but I think that was probably well, no, maybe they got more obnoxious when they developed string theory and claimed to have a theory of everything. Maybe that was the peak of obnoxiousness. But well, anyway, it's certainly. But your initial interest in guts and grand unification was the specific mechanics of. So let's step back again, since this is for people other than you and me. The three non-gravitational forces in nature could become unified, and that meant that at some very small scale, they would essentially be part of a larger theory. And then they would, as the scale increased, or as happens in physics, as the temperature, the energy at which interactions are taking place decreases, eventually those theories would begin to look very different. And in physics, we call that in physics we call that a phase transition. So one had to try and understand how it was that one single theory would break apart into three theories. Now, an example of how it had been done was the electroweak theory that Steve Weinberg and Shelley Glasgow and Abdus Salam won the Nobel Prize for. But it was an example of something that was then adopted at a much higher scale. And was it at this stage when Steve Weinberg sort of began to influence you more? Was it with guts or what? Why don't you talk us through that?
Yeah, with guts, but actually there was a particular interaction which I'll get to in my story.
Okay.
So the sort of the immediate story of how I got into inflation begins when I was at Cornell as a postdoc, and it began really with two events, which are maybe slightly separate from each other, but happened within a few weeks of each other. One was a visit to Cornell by Bob Dickey from Princeton,
Great,
who was one of the
leaders. Should have won a Nobel Prize or two. Yeah.
Right.
Yeah.
Should have, right. One of the things, and he gave a series of lectures, and one of the lectures talked about what, I forget if he used the word or not, but what we now call the flatness problem. And what he explained was that if you trace the universe backwards in its evolution and look at it at a time when it was 1 second old, at that time, if you fix your notion of what the mass density was, the expansion rate had to be just right to an accuracy of about 14 decimal places for the universe to look anything like what it looks like now. The idea was if it was expanding just a little bit slower, the universe would have soon just recollapsed under its own weight. And if it was expanding just a little bit faster, and a little bit means 1 part in the 14th decimal place, just 1 point in the 14th decimal place, if it was just a little bit faster, the universe would have flown apart so fast that no structures like galaxies or stars would ever have formed. So the question was, how did this incredible fine-tuning take place? What caused it? And he didn't really have an answer to that, but he raised the question. And I didn't really understand his calculations or anything. I'm not sure in what detail he tried to present them, but I was very much struck by that fact, which stuck in my brain for a while.
Okay.
Forever, I guess.
Yeah.
Uh,
I learned it from you, I think. But anyway, go
right. Could be, right. But I learned it from Dickie.
Yeah.
No doubt about where I learned it. And then the other event that happened that was crucial is a fellow postdoc at Cornell, Henry Ty, who you probably know,
Of course.
came to me one day, and he, by the way, was also an MIT, a recent MIT PhD. So we had a common background. He came to me one day, and he had gotten very interested in these grand unified theories, which were still at this point very foreign to me. They sounded crazy.
Oh, interesting.
But having gotten interested in them, he came to me and asked me whether or not grand unified theories would predict that magnetic monopoles should exist. And
Okay.
that was the kind of thing that I had worked on in the past when I was doing gauge theories at Columbia. One of the things we worked a lot on were the nature of magnetic monopoles and gauge theories.
Which, in fact, I like to go back to that because when people talk about inflation now, one of the things they don't realize, I think for me, when I first heard about inflation, you know, the flatness problem seemed like something astronomers worried about, but they were all probably all wrong. But you know, if as a particle physicist, that was kind of my attitude maybe. But there was a real problem, and at the time, solving what became known as the monopole problem seemed to me to be one of the strongest features of inflation. And now one often doesn't even hear it talked about. And I'd like to go back and give people a little bit of an education in that, especially since it was relevant to your work. When you were at Columbia, you were thinking about monopoles, and really, so what to put in a framework, of course, the difference between electricity and magnetism is that there are electric charges, whereas magnetism, there are only dipoles. There's little magnets with the north and south pole. And there was a big mystery. Dirac made an amazing proposal, which should have been right, but maybe in the end it may have some.
It may still be right.
It may still be right. That a way to understand the remarkable quantization of charge. In fact, all charges come in multiples of, say, the charge of free particles and charge on the electron, say, could be understood if there was a single monopole in nature, a magnetic monopole. And that was a profound and amazing, very Diracian argument. But it required being put in by hand. But then the real change, and maybe you can walk me through it, was when Gerard 't Hooft showed in one of his many groundbreaking papers in the 1970s, and he really did lead the field in so many ways, that if you had these grand unified theories, what were called non-abelian gauge theories, unlike electricity and magnetism, which are called an abelian gauge theory, these complicated gauge theories that could encompass all the known forces of nature other than gravity, that magnetic monopoles could actually naturally result as real solutions of the theory. When did you first hear about that, and how and what was your work on that? So,
okay, yeah, that's one of the things I first learned when I was at Columbia,
Okay.
and our work was somewhat related to that. You, by the way, didn't quite state it accurately. The original magnetic monopoles were discovered, I guess, independently by 't Hooft and Polyakov. One addition to what you said, but also it was not in grand unified theories. It was in a much more simplified gauge theory.
It was
theory.
A non-abelian gauge theory. That's what I really, okay. Of which ultimately, which is standard, which occurs in even the standard model in the electroweak theory is a non-abelian gauge theory. Yeah.
Right. Although the standard model does not give rise to magnetic monopoles, as you probably know. But models that are not any more complicated can give rise to monopoles, and that's what 't Hooft and Polyakov discovered. And it's exactly what you said, that while Dirac had a theory of monopoles that one could put into the theory by hand, one might say, what 't Hooft and Polyakov discovered is that once you write down this gauge theory, which ostensibly does not have any magnetic monopoles, you can nonetheless discover that there are solutions to the equations that correspond to kind of twisted configurations of fields that form topologically stable knots, and that those knots behave as magnetic monopoles. And once you formulate the theory, there's just no way to stop them from happening. It becomes a particle or a possible state within the theory.
And as particle physicists are wont to do, when there's a particle that comes out of the theory that you can't see, make it heavy.
Right.
And so the idea was that, because no one had ever seen at that time still, and until Valentine's Day a little bit later, no one had ever seen a magnetic monopole, and still haven't. The idea was that they were somehow, if they exist in nature, they were heavy. And you're absolutely right. That the original theory of 't Hooft and Polyakov was a much simpler theory, not abelian theory, very similar to the electroweak theory in some ways, but
Yes.
a different grade group, as we call it. But the great thing was that when you had grand unification, the scale of grand unification was pushed up so that any sort of kind of new particles associated with this unified theory would be at an energy scale 16 orders of magnitude heavier than the proton, or 15 at the time, 15 orders of magnitude heavier than the proton. And therefore, if monopoles existed, they were so heavy that you would never produce them in accelerators, and therefore they weren't a problem ostensibly. But they became a problem. So Henry was the one. Did he? Your focus wasn't on cosmology and astrophysics. I don't know if you were thinking about it at all.
No.
Did sort of, when you were talking to Henry, did he tutor? He was beginning to think earlier on about cosmology, I think, right?
Yes, that's right.
Tutor you in cosmology at all, or did
I was not thinking about cosmology at all.
Did Henry tutor you at all at the time when you were working, or where did you learn your cosmology then?
I probably learned my cosmology mainly, well, let's say, I certainly learned a lot of the background by reading Steve Weinberg's The First 3 Minutes.
Me too. Yeah, it's a popular book, which shows that you can get a lot out of popular books. Yeah, yeah.
But before that, I was certainly dealing with the fundamental equations of cosmology, and probably I learned them from Steve Weinberg's General Relativity book.
Yeah. Again, where I learned
which I still knew from graduate school.
Okay, and then, but Henry sort of convinced you that this problem was worth thinking about.
Well, let me tell in more detail.
Okay, good. Well, that's why I'm asking. I gave you a leading question.
Right. Okay. So I'll follow your
follow the lead.
So Henry came to me one day and asked me whether or not grand unified theories would produce magnetic monopoles, which is not generally known at the time. There were probably other people who knew it because it's a fairly straightforward deduction from things which were known. But I didn't know what a grand unified theory was. So he did have to tutor me about that. And in truth, I remember thinking at the time that I never really understood the standard model in full either. So now I can understand the standard model as a subset of grand unified theories.
Okay. Okay, great.
But in any case, Henry did a good job of educating me on those things. And then it was obvious that, yes, grand unified theories do predict that magnetic monopoles should be part of the particle spectrum. They should be a possible kind of particle for the same reason as 't Hooft and Polyakov discovered in the simpler theory. And also, as you already said, because the scale of grand unified theories is so high, these monopoles would necessarily be at that scale, in fact, even a little bit above the scale of other particles introduced by the grand unified theory. So I told Henry, yes, it predicts they should exist, but these theories are crazy anyway, and these monopoles are even crazier. Nobody has any possibility of ever seeing one, so why should we care?
Why should we care? But did you write that up? Actually, wasn't aware. So did you write, were you presumably the two of you, the first to point out that monopoles were a consequence of grand unification? Did you write that up?
No, we didn't write it up.
You see, I know, Alan, I know you well enough, having written papers with you, that you don't like to write things up.
That's right. That's right. I don't know if we ever looked carefully enough to discover if we were the first people to realize this. Certainly other people did shortly after. So
yeah,
with no harm to the field by our failing to write it up. But when I told Henry that we're obviously never going to see these particles anyway, without missing a beat, he came back and said, well, why don't we try to figure out how many of them would have been created in the Big Bang?
Oh, okay.
And that was the start of everything. That was
now, and that was the start of everything, because it led to did you guys write that up? How many would be created in the Big Bang?
Well, okay, that story has several twists.
Okay,
We started
because I
working.
know, I mean, yeah, okay, go on.
Okay. Well, let's see. First of all, both of us were working on other things, and I thought it was kind of a crazy thing anyway, because obviously these grand unified theories are a stab in the dark.
Yeah.
So I was not too quick to start to work on it. So maybe 6 months or so dragged by um, between, I guess, the fall of 1978 and the spring of 79. And in the spring of 79, here's where Steve Weinberg comes in. Steve Weinberg came to Cornell and gave a series of lectures about his work on grand unified theories and baryogenesis.
Yeah, okay.
You might recall that Steve was one of the first people who worked on that question.
Sure.
How is the net excess of baryons over antibaryons, matter over antimatter, created?
And let me just interrupt for a second to say that in my mind, that was a crucial moment, because that's when thinking about cosmology became kosher for particle physicists, because that was a particle physics problem in some sense that was a problem in cosmology that could only be solved by particle physicists in some sense. And so his work on that and his example of being a well-known scientist made it kosher. I know it dramatically affected me. I was doing my PhD at the time, to be able to think about those questions, apply fundamental particle physics to the universe. Before then, it kind of seemed like science fiction. You could go back to a second, but that wasn't really particle physics. But anything before that was kind of just, science fiction. But here was a real problem and a crucial problem. Why is the universe made of matter, not antimatter, that had no solution, and it had to have a fundamental explanation in terms of particle physics? And he was one of the people who spearheaded that. So sorry, go on. I thought I just put that in perspective.
Yeah, no, I completely agree with you. Thanks for saying it.
Yeah, okay.
And the effect that you described is exactly the effect it had on me.
Okay.
So while I had been dawdling about thinking about these things, and maybe we should emphasize to the audience that we're talking now about time scales in the early universe, like 10 to the minus 35 seconds, decimal point 34 zeros.
Yeah.
You get very tired writing finally a one.
Yeah.
It's just unimaginable that one could talk about such times, and it had seemed totally crazy to me because of these unbelievably early times that we would necessarily be trying to make statements about. But after Weinberg's visit, I decided, well, if someone of Steve Weinberg's stature can work on this, why should I? And that's really when Henry and I got to work on trying to figure out how many magnetic monopoles would have been created in the Big Bang if grand unified theories were a correct description of particle physics.
And you wrote that up?
Eventually, yes, but well, not exactly, actually. Again, this is a story of many twists.
Okay.
We fairly quickly, and I don't remember exactly how long, maybe a month or something like that, came to the apparent conclusion that far too many magnetic monopoles would be created, that the universe should just be swimming with magnetic monopoles, with a number of magnetic monopoles comparable to the number of protons. And there obviously aren't, because we don't see them. But even beyond that, was a fun calculation that we did at the time of the effect that this would have on the age of the universe. The magnetic monopoles weigh about 10 to the 16 times as much as a proton. And if there are comparable numbers, that would mean the mass density of the universe and these hidden monopoles would be vastly larger than we imagined the mass density of the universe to be. And that would mean the universe would be slowing much faster in its expansion from the Big Bang. And that would make the universe, given other observations, fixed vastly younger than you would have thought if you do not include these monopoles. And it ends up being about a week old.
Which was, and there was reasonable evidence that it was older. Just from your postdocs, actually.
That's right. That's right. Just from my postdocs.
Right.
But we thought it was cute that it came out to be such a biblical number.
Yeah, exactly. In fact, actually, I'm surprised you weren't adopted by the by the biblical creationists. But yeah, a week old, that'd be perfect.
Right. So we were convinced that there had to be some mechanism that prevented this magnetic monopole glut. But we were scooped on publishing that. So in fact, we didn't publish exactly that.
Well, it's John Preskill, when I, that's where I learned. I mean, he was a graduate student around the same time as me, a little bit earlier, but and he, he produced the paper, at least showed the problem and of the
Yeah.
fact. I wasn't clear to me who showed how many there would be, but what he worked out in detail was that, the only solution to that is to try and get rid of them, if they could somehow get rid of each other, annihilate or something. And in a pretty lovely paper,
I agree.
demonstrated that any kind of mechanism you could think about would not get rid of the lot of them early on. Had you worked on that part too, or you just worked on the production of them, or did you think about getting rid of them as well?
My guess is that we didn't think about getting rid of them until we read John Presco's paper. I'm
Okay.
not entirely sure, but I don't remember trying to get a handle on that.
Okay, but that created this.
That was one of the fuzzy issues for us, which is
Yeah.
why we didn't publish immediately.
It required a lot of different thinking. I remember being impressed by the paper, a lot of thinking from different parts of physics to try and decide whether monopoles you could get rid of. And it was very powerful arguments and convincing arguments in general. And I've written papers since then on ways to try and get rid of them. But you have to sort of stand on your head. But that created what was then and increasingly seen, at least to me as a graduate student and around that time, I was still a graduate student, an emerging problem that was severe. That particle physics predicted, if these grand unified theories were right. I mean, it was another reason for me to perhaps not believe in grand unification, is to say, if these theories are right, they'd produce something that clearly wasn't there with such abundance and it wasn't there, and that suggested the theories were wrong. It was a really clear and pressing problem, at least for some people who were beginning to think about cosmology, as I was at that time, and you were. But that's
Right.
what really motivated, is that, well, anyway, so let me ask you, was it, the paper you eventually wrote on inflation was written as a solution to the horizon and flatness problems, I think. I don't think monopoles were in the title at all, right?
They were not in the title, but they were in the
In
article.
the paper, yeah. So were you thinking about, so what led to the realization that how can I put this? You weren't really motivated in developing inflation, the realization that inflation happened, that the universe could expand exponentially naturally as a result of a phase transition in the early times that might be associated with grand unification. It was kind of a natural expectation that could easily happen, and it would solve all these problems. But was it more the flatness problem that you were thinking about at the time than monopoles? Or why don't you walk us back? And I'm sure this is a story this particular story you've told a gazillion times, but why don't you walk us back through that? I like to in these things to try and focus on things you haven't spoken out a million times, but okay.
Yeah, well, after John Presco's paper came out, Henry and I felt scooped, but we wanted to try to salvage what we had done. We didn't think it would be appropriate to just publish another paper saying we found independently what John Presco found, especially since we think his derivation, at least I thought his derivation was better than anything we had at the time. So we decided to concentrate on the question of whether or not there's any way around this problem. Is there anything we can introduce to change either grand unified theories or one's model of the early universe to make grand unified theories consistent with cosmology? And now there's sort of two parts, the part that Henry was part of and the part that happened as he was leaving on a trip to China. But while we were working together, and this did lead to a paper that we wrote together, we came up with the idea that extreme supercooling at this phase transition could prevent this magnetic monopole glut. The idea is simply that the excess of magnetic monopoles happened because the magnetic monopoles were described in these theories as twisted knots of fields. And if the phase transition happened quickly, people had been assuming, and we assumed initially, that the phase transition happened instantaneously when the temperature fell to the right value. Then there's not time for these knots to smooth themselves out, and you end up with a very knotty field, which means a large number of magnetic monopoles. But if there was a huge amount of supercooling, so the universe cooled to temperatures well below the natural temperature for the phase transition without the phase transition happening yet, and that's always a possibility. Then there'd be time for these knots to smooth themselves out before they get ironed in. And we argued that that could be the explanation of why there's so few monopoles. While we were doing this work, and in the paper that we eventually wrote, we were really blindly assuming that as the supercooling was taking place, the universe would go on expanding exactly as it would have otherwise.
Which of course is wrong.
Which of course is very wrong.
Yeah.
I'm pretty sure it was Henry who told me that I should look at that. And what happened is one night in December of 1979, I went back to my rented house. At this point, I'd moved to Slack for the year. So I went home to my rented house in Menlo Park, California, and wrote down the equations on a piece of paper. And as you know, but the audience may have trouble believing, once you write down the equations, it's just so obvious. That the real question is just, why wasn't it obvious to everybody before this?
By the way, you've probably heard this, but I know many of my colleagues, well-known physicists, a number of whom won the Nobel Prize, who've all said the same thing to me. Why didn't I realize that? No, because it's amazing when you look at it. It's one of those things where the minute you see it, it's just so clear.
Yeah. Right. It's very simple physics. It's a differential equation you could show to a freshman, and the freshman would know how to solve it.
Yeah. It's weird that, and you don't take things. It's often, in fact, I've often said this about, and this is an example where maybe it was cosmology that forced it, but I found in my career, and I guess I've done a lot of things that are more related to, at various times, to particle accelerators than you have, but it wasn't until there was a real experimental problem that I began to think seriously about the theory. There are papers I could have written well in advance of an experimental development that I never thought seriously enough about till the data showed it to me. And I guess maybe that was an example. People didn't play with the idea until there was a real reason to think about that problem. And that's why I wanted to bring up monopoles in some sense, because while history now doesn't use them think of them as a key, but it was that real problem in some sense that caused someone like you to think seriously about the equations.
No, definitely. It was definitely magnetic monopoles that got me into this. It was only after, on that same night, but after I realized that the system is going to start exponentially expanding, that I realized that it would solve the flatness problem too. And that got me extraordinarily excited.
Yeah, I bet. Everyone's seen your notebook with the exclamation marks.
Right, and the double box.
Yeah,
right. Exactly.
And then the horizon problem was later, and we'll have to frame that for people. But it's a more subtle. Well, in some sense, it's a more subtle problem, but it's an important one. And of course, inflation naturally solves that too. And do you want to explain that?
Sure. The horizon problem is the problem of understanding how the universe got to be so uniform. And this uniformity is seen most clearly observationally through the cosmic microwave background radiation, which of course we view as the afterglow of the heat of the Big Bang. So it fills the universe, and we see it coming from all directions. And when we measure its intensity in different directions, we find that after we correct for the motion of the Earth through it, which changes things a little bit, it's just unbelievably uniform, same in all directions, to an accuracy of about a part in 100,000, which is incredibly uniform.
Incredible, unbelievably.
Yet, it was pointed out long before my work in cosmology that if you trace back these photons of the cosmic microwave background that are arriving at Earth today from two opposite directions, trace them back to where they came from, when they originated, those 2 points were separated from each other by roughly 50 or 100 times the distance that light could have traveled up until that time. So there's just no way that the point over here could know anything about the point over there, but somehow they sent out photons that agreed in temperature to an accuracy of 1 part in 100,000. And that's an incredible mystery when you think about it.
And Was it Jim Peebles who? I mean, I learned that I think from Peebles first, but I don't know who first
Who
pointed out
first
the
pointed
horizon.
out the
I mean,
problem?
there were people who thought about it, but um, and again, I think it was one of
I
those
think
things you don't take
Rindler is
seriously.
often.
What was that?
I think Rindler is sometimes credited
Rindler?
as the first
Okay,
person.
okay.
Um,
And again,
some people
it's one of
still.
those things you don't, you know, uh, to try and again frame for people the transition that occurred in the way people thought about things. It was an understood problem, but no one thought seriously about applying fundamental physics to the early universe. It just seemed so crazy that I think people said, well, yeah, that's a problem, but there's so many other problems. Why worry about that one? Because it's not a big deal. Yeah.
Yeah, yeah. No, that's right. People did not take it terribly seriously. At least particle physicists did not take
Yeah.
it seriously at all. Some people were thinking about cosmology, were puzzling about it, but didn't really have a handle about what to do about it.
So you realized it solved the horizon problem after you realized it solved the flatness and monopole problems. Is that
That's
correct?
right. In fact, I only learned that the horizon problem existed and did not invent it myself. So I learned it from others.
Yeah.
And that only happened until a few weeks after. It was all rather coincidental that it all happened within a few weeks. But a few weeks later, I was having lunch at the cafeteria at Slack, and group at the lunch table was having a conversation about the horizon problem, motivated by a paper that had just come out by Tony Z.
Uh-huh.
And I don't remember what kind of a possible solution he was talking about, but he did bring up the problem and cause our lunch table to talk about it. So I asked the people at the lunch table, what is this horizon problem? And they explained it to me. And I don't remember how long it took, but certainly didn't take very long before I realized that, yes, inflation gets around that problem too.
Well,
So
okay,
I added
now,
it to my list.
yeah, no, then you were very excited, but I'm still, we'll get, we'll get to something that's again uniquely Alan Guth like, it seems to me, but we'll get there. I mean, knowing you as I do, but before we do, let's explain to people, and that means let's you explain to people, uh, uh, why inflation solves all these problems. So let's give a little
Oh,
brief
yeah, sure.
primer.
Okay, brief primer of what inflation does and
Yeah.
how it solves these problems. Um, okay, looking back at it rather than giving
Hmm.
the historical
Sure.
narrative that we just talked about, inflation, I think, is the best way to start to think about it is as an answer to the question of what drove the Big Bang. What was the repulsive force that drove the universe into the gigantic expansion that we're still seeing the aftermath of? Curiously, the theory called the Big Bang Theory says literally absolutely nothing about what caused the expansion.
Yeah.
The Big Bang Theory, as it existed before inflation, was purely a theory of the aftermath of a bang. In its description of the universe, it starts with the universe already uniformly expanding. And how that happened, there was no previous explanation. Inflation explains this through a repulsive form of gravity. Now, repulsive gravity is certainly not widely known among the public, and certainly never taught to me when I was in school. Newtonian gravity is entirely attractive. Two masses attract each other always, never the other sign. But in general relativity, it does turn out, and this was known really from very early on in Einstein's work, general relativity can produce repulsive gravity as well as attractive gravity. And the key is that in general relativity, gravitational fields are produced not only by mass densities, which are equivalent to energy densities with E equals mc squared, but not only is it these mass densities that can create gravitational fields, but pressure can also contribute to the gravitational field. And that's built into general relativity at the heart.
Yeah, and it's very hard because it's because of its because of the structure of space-time. Yeah.
Yeah,
Okay.
yeah. Maybe since you started, we'll elaborate a little bit on that. If general relativity was designed to be consistent with special relativity, and in special relativity, if you know the energy density in one frame, that's not enough information to know the energy density in another frame. And transforming between frames is crucial. So one always has to be explaining things in terms of quantities that can allow you to know what happens in one frame in terms of what happens in the second frame. So to make the energy density complete, you actually have to combine it with 9 other quantities. But if everything is spherically symmetric, it is just the energy density and the pressure that survives. So we'll work in that simplification. If everything is spherically symmetric, and I know the energy density and the pressure here, I can talk about a moving frame and I know what the energy density and the pressure is there. So pressure is necessarily part of the equation. And it's this whole, what's called the energy momentum tensor, that is the source of gravity in general relativity. So it includes both energy densities and pressures. And energy densities, as far as we know, are always positive. One can build theories of negative energy densities, and they may happen as quantum fluctuations, but nonetheless, they don't happen big time, and they're not relevant here. But pressures can actually have either sign. They can be positive or negative. Now, we're accustomed to thinking of pressures in an ideal gas model where they're caused by particles bouncing off the wall, and that seems to only allow a positive pressure. And it's true that that model only allows a positive pressure. But you really don't have to go very far to see the possibility of a negative pressure. The simplest example that I know of is to just imagine a piece of rubber, and to keep things isotropic, same in all directions, imagine pulling out in all directions on this piece of rubber. It will pull back. That's negative pressure.
That's right.
It's not large enough to see the gravitational effects of it,
Yeah.
but it is negative pressure.
Well, that's a good example. Okay, that's good. I like to say, I've always said that my short version of what you just said is that gravity doesn't always blow. Sometimes it sucks.
That's right.
Yeah.
That's right. Exactly. Your short version is very accurate.
And but I think
suction is the right way to look at this negative pressure.
But to put it, the framework, this sounds very mathematical to people who are listening, and it is. But I think I want to put it back in the framework. What you realized was that the specific conditions for energy and momentum, when you're in the middle of this supercooling phase, when a phase transition hasn't completed, when there's energy density that's stuck in empty space, if you want to say it, because that hasn't yet been released, because the field has not yet cooled to its, or not yet relaxed to its preferred state. So it's storing energy that really doesn't want to be there. That particular type of energy momentum was exactly the kind of energy momentum you're talking about, which had negative pressure.
Exactly. Yes. What you just said is absolutely right. I would have said it next.
Oh, sorry. Okay. Well, I wanted to lead us back in, and now let's your turn.
Right. Yeah, okay. I go off on tangents. It's true.
No, it's sorry. No, it's great. Tangents are often more interesting than. No, it's good.
Right.
Okay.
Right.
Okay.
So this supercooling leads exactly to that kind of state with a large negative pressure. In fact, the pressure is almost exactly equal to the negative of the energy density. And that turns out to be more than enough negative pressure to drive the region through the gravitational repulsion into a phase of exponential expansion. And in case any of the listeners don't know, exponential expansion means that in a certain very small amount of time, the region doubles in size, and then in the same amount of time, it doubles again, and then doubles again, and then doubles again. And these exponentials build up very quickly into very large amounts of total expansion.
So the universe could have, just to give people a sense of this, in 10 to the minus 35 seconds, the universe could have expanded by how much?
Yeah, kind of the minimal numbers to make inflation work at grand unified theory scales is about 100 doublings. And the time period might be about 10 to the minus 35 seconds.
And for people to understand, 100 doublings is about 10 to the 30th, right? Or something like that.
10 to the 25.
10 to the 25. So I mean, that's amazing to think about. It's still one of these things that it can happen, but it's hard to imagine actually did happen. The universe could have expanded by a factor of 1 with 25 zeros in a time frame of 10 to the minus 35 seconds.
Yeah, that's right. Now it's mind-boggling, which is why it took me so long to take it seriously myself.
And now, so why does that solve the problems? So
yes,
how does that
okay. Right. No, they're fairly simple explanations for how it solves all three of these problems. Let's start with monopoles. it solves the monopole problem in a very simple way, really. The monopoles are produced dominantly when you reach the critical temperature, but then we're going to have this huge amount of exponential expansion after. So it doesn't actually lower the number of monopoles that are produced, but what it does is to stretch space out by this factor of 10 to the 25 or so, diluting the monopoles fantastically. So you start out with a glut of magnetic monopoles, but by the end of the exponential expansion, the density is entirely negligible.
You probably have
never
one
expect to find
at
any.
most, and it was probably, and it might have been discovered at Stanford in 1982 by my friend Las Cabrera, but none. But generically, I think it would be one, right? I mean, universe would be less than one horizon region, so it'd be one monopole at best in the whole universe, right?
Yeah, I think they're even less.
It's much less because the horizon's much bigger, but
Yeah,
but
right.
Yeah, but one
Right.
is one at most.
One being
perhaps.
upper limit, right?
Yeah.
Yeah,
Anyway.
one would certainly be an upper limit. And you're right. It might be that one that was found
1982 on
Valentine's Day, 1982,
Yeah.
but most likely it wasn't.
Yeah. Anyway, so the monopole problem is immediately solved by just diluting them away.
Right.
Flatness and horizon?
Okay. Horizon is similar, really. I'll do that next. The horizon problem, the way I described it, you'll recall, is that if we follow two photons backward, two photons of the cosmic microwave background arriving from opposite direction, we follow them backwards to their source. Those 2 points were separated from each other by far greater than there could have been any communication between those 2 points in the conventional cosmology. What inflation does is it adds this period of exponential expansion. And that means that if we follow the observed universe backwards in time, when we come to the inflationary period, that looks like exponential contraction going backwards in time. And it means that before inflation started, in the inflationary model, the region that is destined to become our observed universe is vastly smaller than anybody had previously thought. And it's while the universe was so vastly small that there was plenty of time for everything to become uniform, plenty of time for light to cross that region zillions of times over and smooth everything out. And then once the smoothness is established, inflation takes over and stretches this tiny region to become large enough to include everything that we see. So the uniformity is just preserved by that stretching.
Mm-hmm. And we'll come back to that in a number of contexts. But okay, but that's great. And then the flatness problem.
Flatness problem is, I think, most easily understood by imagining, for example, that the universe might be closed rather than flat. So here's our closed universe. All inflation does there, it's really very simple again, is it stretches it fantastically. And if you look at a tiny patch of the surface of a sphere, it looks flat, just like the Earth looks flat to us.
Yeah, Kansas. Yeah. Okay, and it's that simple. It naturally solves these three fundamental problems, and the key thing that I want to stress here, and is that it's natural. It's not. It's sort of. It came out of thinking about a theory that had not been designed to explain the universe in any way. If anything like grand unification, or if there were phase transitions in the universe, which are again generic because we know there was one that separated the weak and electromagnetic interactions. We know that such things happened in the early universe, that this is kind of the rule rather than the exception, that something like this is generic, and it's almost impossible to imagine that it couldn't happen if you had phase transitions. And you would sort of, you would agree with me here, because I know I've sort of, people have been beaten up on me by being a little bit hard on Roger Penrose when I was talking about this subject, but I really want to stress it because I think it's true that this is kind of a generic behavior that is not at all invented to somehow solve some problems, but it's a behavior that happens and it turns out to solve the problems.
Yeah, no, I think that's entirely right. And I maybe should add, to make Andre Linde happy, that it's even a little bit more general than what you described. Everything you said is true. But even without phase transitions, if you have a potential energy surface in field space, describing the potential energy as a function of the values of fields, whenever you have a hill, if you start on top of the hill, which if you have random fields in the early universe, you'd expect somewhere it would start on top of the hill, you can roll down the hill in exactly the same way. And you don't even need hilltop. If you have a hill,
a valley,
if you start high enough on the hill, it was Andre Linde who pointed this out. If you start up high enough on the hill, even if you don't have a plateau, you could still have inflation as it rolls down and produces all of these same
Yeah,
solutions to these problems.
yeah. In fact, a very important kind of inflation that he would. Yeah. Well, we'll get to Linde and that. And one of the things I should say is this statement about there's enough time to solve the horizon problem is something we'll come back to, because I do want to talk about sort of the discussions you've had about Roger Penrose's concerns about inflation, and that in some sense they come back to that question of that early time, whether there was enough time to get things uniform. So, but we'll get there. I So that's inflation in a nutshell, which I think is essential to talk about, because I want to spend time now talking about the more subtle questions that are still open questions. The beauty of inflation was there immediately. It did, if nothing else, it got you a ton of job offers. Finally, in a field where it was hard to get a job.
Right.
And I remember how hard it was to get a job back then. But I got to ask you this, and this is what I mean by the prototypical Alan Guthian thing. You first talked about inflation in January 1980. This amazing thing. And the paper appeared 9 months later.
Yes,
were you just too busy talking about it? I mean, everyone knew. I knew you'd been doing it, and I hadn't. I'm pretty sure I knew you'd been doing it before I ever saw the paper. I don't know, but you obviously started talking about it and must have gotten a lot of requests to talk about it. But what was the reason for the delay?
Well, two reasons, I guess. One is just the Guthian aspect of it. I do write slowly and try to make sure every word I say is accurate.
Yeah, you do. That
but-
is a characteristic of you, which I've admired tremendously. You try to make sure everything you say is precisely accurate, and often catch me when I'm just sort of, approximating things. So I really appreciate that. But go on.
Okay, but there was another significant reason, which is that when I started giving talks about it in January 1980, I could point to these wonderful successes, which I thought was real, and a lot of other people got very excited about it too. So it really did catch on very quickly in the particle theory community. But there still was an unsolved glitch.
Yeah, a real problem.
In the end, which is, how does inflation end? The assumption that I wanted to make at the end of January, but I knew I couldn't show, was that when the phase transition finally happened, it would happen by bubbles forming in different places randomly, as is supposed to happen in a first order phase transition, and that these bubbles would then grow and collide and merge. And the hope was that they would merge smoothly enough so that it would be compatible with the smoothness of our universe. Inflation clearly created fantastic smoothness, which was one of its wonderful features, and that's more or less the horizon problem. But when inflation ends, it clearly creates a certain amount of chaos, and I didn't know if that would work out right or not. So most of the spring, while I was traveling around giving talks, I was also worrying about this question and talking to a number of people at the places I went to give these talks. And in fact, I acquired the crucial piece of knowledge to understand this problem at Cornell, talking to, what's his name?
Not Hans
Okay,
Bailey.
I'm gonna take a pass.
Okay, it doesn't matter. Don't worry about that. But the thing is, I mean, it's a natural segue. This was a real problem, and in fact, there was no. I mean, within the context of the original idea, there was no solution to that problem, and I suspect you were one of the people who showed that, right?
Yeah, well, that's right. With the help of this mathematician at Cornell,
Whose name
I can't remember.
unheralded, but a mathematician somewhere.
Right.
Who
Right.
he can write me
He
later.
declined our offer to be on the original inflationary paper.
Okay.
But it was his insight that allowed me to show. I just had to extend it a little bit, really. He showed more or less on a checkerboard model how this system like this would work, and I filled in crossed the T's and dotted the I's to show that it would work in a three-dimensional model as well. So the bottom line is that in the original model with the strongly first order phase transition, it really just did not work. This
So that's amazing. I mean,
came to be called the graceful exit problem.
yeah, that's what word I have down, the graceful exit problem, which you showed there was no graceful exit. And it's amazing. I mean, that must have been a huge disappointment. I mean, I know it's an experience I think a lot of us theoretical physicists have had. I've had it numerous times when I was a kid, where you come up with an idea and it looks to you to be great, and you think, oh, it's all, and then it craps out, and you know,
Right.
"Oh, this is just going to do everything. Oh no, and the good thing about science is that scientists, when they realize that, they generally are honest about it and don't try and sell it. I know some people who haven't been, but but and you just have to say it doesn't. You know, it's a neat idea, but it doesn't work. But it's actually useful to publish neat ideas that don't work because it motivates other people to think about ways that might work, or at least, you know, and so I've learned that. There are a lot of times I never published something and I realized I wished afterwards because it became significant. At the time I thought it's just not going to work. Um, but you published it, and was a big disappointment to you at the time, or did you just at that time had you been such a convert that you knew there had to be something? It
Uh,
smelled too right.
I was still pretty confident that it would hold up in the end. That it just seemed to have too much going for it.
Yeah.
And certainly the failure at the end of the inflationary period is separated in time from the success at the beginning and during the inflationary period. So I did have significant hope that somebody would find a better ending and that the whole thing could be made to work. But of course, I was disappointed. I certainly would be much happier if everything had fit
Yeah,
together
yeah, yeah.
from the beginning.
But it's interesting. It was such an amazing idea that already before anyone knew how to get out of inflation, and before anyone found a graceful exit, you had already. I mean, that your career was now. I mean, you already had numerous job offers, and I was around. I was in Boston, and every place I was at, whether it was MIT or Harvard, was talking about who would try and get Alan Guth there at the time, and and so yeah, it was that significant that there was a phase transition in the physics community that suddenly I think everyone thought that this is just too good an idea not to be true. And by the way, it was interesting as a physicist versus astronomers, and because most of my after that my career, I've always been in both departments, and for a long time it was kind of interesting to see that the physicists had already decided the universe had to be flat because that was a generic prediction of inflation. And while we'll point out that inflation can do many things, and when it didn't look like the universe was flat, a lot of people came up with inflationary models that didn't produce a flat universe. But those I would think are fair to say are the exception rather than the rule. Um, but the astronomers, that's garbage. They didn't believe the universe was flat, and at least for a long time. And it was an interesting bifurcation that the theoretical physicists were so enamored with this idea that they were convinced, even in the absence of any evidence, the universe had to be flat. It's really kind of amazing. So the physics community was convinced that it was great. You got a job, and then what happened?
Well, let's say in terms of the theory development,
Yeah,
the next very important step was one that
yeah,
did not involve me, except I read about
yeah,
it,
yeah.
which was the discovery of what was initially called the new inflationary universe, which was the first solution to this graceful exit problem. It was discovered independently by Andrei Linde in the Soviet Union and Albrecht and Steinhardt at the University of Pennsylvania. And the idea was that instead of having the phase transition happen sharply by the formation of many little bubbles, which is what we call a first order phase transition, it would be a type of second order phase transition. The way it was often described at the time, which I think is still good, is it's a phase transition that's more like the congealing of jello than the boiling of water, something that happens gradually over a region of space, more or less uniformly. And that could produce regions of uniformity more than large enough to describe the universe that we observe.
So the simple way to frame that for people is to say that instead of being many bubbles of new phase forming, our universe existed inside of one bubble,
One
and
big
that
bubble, right?
and that by the way, is one of the reasons one could argue that there's not more than one monopole in our universe because the monopoles tend to form at the intersection of bubbles, and And so that was a complete, and that's generally, that's the picture that, then that works. At least it works in principle. We'll get to the fact that, well, I want to ask about your biggest disappointments and your biggest excitements, um, regarding inflation before we move on. But, well, look, let me ask you, I'm going to lead you rather than, well, maybe I shouldn't, but I'm going to lead you.
Go ahead.
Some people could say, well, inflation is a post-diction. Look, these problems and inflation solves them, but what the hell does it predict? And the real surprise to me, and I want to ask if it is to you too, and you certainly could say no, was a surprise that came a couple of years later, and a surprise I'm very sad about, because I was at Harvard at the time, and I was invited to this meeting in Cambridge, and Harvard wouldn't pay for me to go.
Oh,
And
really? Oh,
and it seemed like at the meeting, everyone who was at the meeting basically wrote a paper on this subject. But and you certainly did. But the real surprise, which really to me smacks, it's when a theory makes a prediction that you didn't expect, and not that solves a problem, but when it makes a prediction and then it's shown to be correct. And that was this prediction that the universe wasn't exactly smooth. The biggest mystery in some sense in fundamental physics, if you think about it, was not, was why are we here, which is not why is the universe so smooth, but why isn't it exactly smooth? What caused these small lumps that eventually became galaxies? And no one had, and I think it's fair to say no one had ever expected, other than having a theory of everything or a religious experience saying God did it, to have a fundamental physics understanding in our century of why this might happen. And what you showed, and others, is that it's just quantum mechanics. If you have inflation and you have quantum mechanics, boom, and you get something which is later on been seen in the microwave background, a small, beautiful, what's called isotropic spectrum, but a scale invariant spectrum, as it's called, and we don't have to go into those details too much, which has been the subject for observers of Nobel Prizes. But it's a generic prediction of inflation. So do you want to, was that, for me, that was the biggest surprise or the biggest thrill. I don't know if for you, was it a bigger thrill to discover inflation or to discover that inflation predicted those? That's what I wanted to ask you.
a little hard to say, I guess. The story of the density perturbations is one that I think drags out over a much longer period of time.
Yeah.
The calculations were done actually in an incredibly exciting way at this Nuffield workshop that you alluded to.
Yeah.
It was an unbelievably exciting meeting because there were 4 different groups there working on the same subject.
Yeah.
We would talk to each other late at night and compare notes. And initially, people got all kinds of different answers. But by the end of the meeting, we all agreed, and we all went out and wrote 4 different papers giving the same conclusions. And that really was extraordinarily exciting. However, at the time, at least in my own assessment of the problem, it was only a game. I never believed that anybody would ever measure these crazy things, these tiny fluctuations in the cosmic microwave background radiation, fluctuations that are only 1 part in 100,000 of the radiation itself. And the radiation itself had only been discovered a decade before because it was so faint. It was very hard to see.
We figured that you'd never be visible because even if it was there, there'd be just too much garbage out there to get in the way. I mean, astrophysics full of dust and all sorts of things. I for one never, and I ran meetings on the subject, but I never felt that the observers would ever be able to disentangle all the noise and get to the signal.
Yeah, exactly. Me too. So I was shocked when Kobe came along and gave the first measurements of these non-uniformities, and then more shocked with balloon experiments like Maxima that showed the evidence of this first peak in the spectrum, which was also a key prediction of inflation, where that peak should be. And it seemed to be right where it was predicted. And then WMAP and then Planck and a number of other ground-based measurements. Incredibly exciting. I completely agree. And I also agree that certainly when inflation was first put together, when I wrote my first paper, none of this was anywhere near anything I was thinking about. So it really was a surprise.
It was a surprise. And it really, I guess to me, when I think about theories, as I say, the fact that when a theory you invent for one reason comes out to have an explanation of something else that's right, it really makes you, if you didn't have some kind of faith, if you want to use that word, and I hate to use that word, but that the theory was right, when it starts making other predictions that of things and they turn out to be right, it really gives you great confidence. So I guess for me, it's hard to know. I mean, there's a great excitement about inflation, and I think it was really more particle physicists again patting themselves on the back, saying we've got a great theory of the early universe. But whether you really believed it, it just, hey, we can do this, was what the excitement about it. But then it was, I think it's really the fact that it predicts what's been seen that really is more convincing that, hey, it's really probably right.
Yeah, no, there is an incredible amount of detail that's seen in the cosmic microwave background. And it's even more than the cosmic microwave background. The fluctuations continue to shorter scales with the baryon acoustic oscillations and Lyman alpha forests. And the predictions of inflation seem to work wonderfully.
They work very wonderfly. Now let's I want to put the devil's advocate, or I want to put a perspective on this, because you might say, if it's so great, why why isn't won the Nobel Prize yet, and all this other arbitrary prizes. You've won a lot of prizes, so that's okay. But it's fair to say, first, it's interesting to me, again, it's sociological, that while inflation predicts it, other people had basically said the only kind of spectrum you could have that's consistent with observations without knowing why would be the spectrum that's seen. So it's kind of, in some sense, the cosmological theorists had already said this has to be what's there, because anything else would have been long inconsistent with either too many black holes or too much stuff that you would have seen already. So the fact that it kind of had been guessed in advance might have been one reason people would say, well, obviously any mechanism has to produce that, and sure, inflation produces it, but maybe there's some other mechanism that produces it. I think it's fair to say, from the sort of devil's advocate point of view, saying, well, yes, this is one example, but how do we know it's the right example? Okay. The other one is I think my biggest disappointment about inflation, and I want to see if it's yours. And people get mad at me for just not asking you and throwing this out. Why? But is the fact that there isn't, it wasn't like the standard model that there's some model that works. Is that with inflation, there's a whole lot of models, and some of them work, some of them don't, but none of them, it's not as if everyone pointed to say, that's the particle physics model that clearly produces inflation. It's obvious, that's the fundamental physics. There hasn't been such a thing. And I think that's, for me, been the greatest disappointment. I don't know how you feel about it.
There certainly was a stage in the development of the standard model where it was the same.
Yeah.
There are a number of different field theories that were being considered. Quantum field theory itself is very flexible. And the physics of inflation is really just quantum field theory plus general relativity.
Yeah.
So it has all the flexibility of quantum field theory built into it. So it is true that one can produce inflationary models which have rather different predictions from others. Surprisingly, I think what we're seeing in the universe is really the predictions of the simplest possible inflationary models, which to me is kind of a miracle. Didn't have to be that way.
It certainly didn't.
Inflation could be entirely right, but it could be a much more esoteric kind of model that is producing the inflation. So I think it's going to be a very slow process to narrow down the physics of what drove inflation to a specific model. It may take a century to reach a specific model. I don't know. It's hard to see how we could reach a single model anytime soon.
But did you think,
for now it's a class of models?
Yeah, but that's a kind of, I agree, that's a sage analysis. But did you think maybe that early on that there might be a single model that would jump out, that it would, that would seem so obviously right? Or was that, just asking, didn't?
Yeah, well, I guess I think probably you're asking me to think back about my own beliefs in technology as time evolves.
Yeah, it's hard to remember what you thought back then.
I think the answer is that I probably did believe that through the calculation of these density perturbations. And what I believed is that the SU5 grand unified theory had to be it.
Yeah.
Because it was just so simple and so elegant and
Yeah.
seemed so much the natural extension of the standard model of particle physics.
Yeah.
But then, of course, that ran into trouble in several ways. The prediction that the theory made for the lifetime of the proton got shown to be wrong. And also, from the point of view of density perturbations, the initial calculations we did of density perturbations show that they were of the right form, as the predictions had the right form. But when applied to something like the SU5 grand unified theory, it produced density perturbations that were far too large.
Mm-hmm. Yeah.
So it had to be some other theory.
Yeah.
And I think at that point is probably where I realized that even though we were pretty lucky with the standard model and guessing the right Lagrangian fairly early in the history of it, it might take longer this time.
Yeah, no, that's right. I mean, it's worth talking about this in the psychology of the field. I think in 1980, and between 1980 and 82, this one grand unified theory looked just so clearly right and so simple that everyone, I think particle physicists assumed it would just be a matter of time because there was actually a way to look for it, the decay of the proton, that it would be seen and everything would fall into place. And then it wasn't. And then things started getting more complicated, and not just in inflation, but in particle physics itself. And particle physics has also moved in the direction of not knowing what, if any, kind of grand unification happens, and lots of additional complications that have caused physicists to look in lots of directions, including string theory. But so that same kind of initial optimism has sort of diverged into realizing that it's got a lot more I was going to say a final solution. I don't like that word, but that if there is a final solution, it's a lot more complicated and a lot longer road to get there. And many people, myself included, I'm not sure that's the right way of even thinking about things. But anyway, so
while we're talking about that, though, let me mention one other big shift in my own faith and guesswork in theoretical physics is, as you might guess, the cosmological constant. The fact that the vacuum energy appears to very distinctly not be zero, while until 1998, I was very much convinced that there was only one simple solution to that question. It had to be zero.
I mean, that was
when it was discovered to be non-zero. And
that
even further blew apart any faith I had that we could just guess the laws of physics.
Yeah, no. I mean, and obviously that hits home for me because, as you know, as you may or may not remember, I proposed that the data had told us the cosmological constant wasn't zero in 1995.
That's right, you did.
But the only reason I did it was, I mean, besides the fact that the data, in my opinion, pointed that way, was because I was convinced some of the data was wrong. It was really a paper to say, look, this is so stupid and so crazy that some of the data must be wrong. And no one was more surprised than me than when it worked out to be exactly what we said it was in 1995. I mean, it was really because it just is so crazy. You're right. And that was the other big surprise. It's changed things. But in a sense, however, it validates inflation as an idea as well, right? Because we now know we live in a universe that's inflating, albeit at a much smaller rate than the one that you argued would solve the problems of cosmology. But we are living in an inflationary universe right now, right?
That's right. So it's a clear demonstration that it's possible, although I think most theoretical physicists never doubted that it was possible. So that's not too big a thing among theoretical physicists. But as far as selling the idea to the public, it probably helps a lot to be able to say, well, I know that the universe is inflating now.
It does. But of course, that leads to another question. And I want to start talking about sort of these open-ended issues, some of which will lead us to Penrose in the last, if you don't mind, maybe 15 or 20 minutes of this or so. We'll do 2 hours or so. It does, the minute you say that, of course, you remember the public or anyone, you think, well, okay, the original inflation ended. What's going to happen in our universe? Is that going to end? And it really depends on the amazing thing is that most theoretical physicists somehow think, or I'd say the majority, think that what we're seeing now is this fundamental energy of empty space and not something that's stuck in a field that's going to have a phase transition, but it could. And I don't know if you have any thoughts, or if you have any, since we've now established that we're all crappy at guessing what the actual answer is. It's
That's
fair to
right.
say.
Now we can guess.
What's your bias? What do you think? Do you think
Uh,
it's fundamental, or it's something that may one day dissipate?
um, I'm not sure if I would describe it as fundamental, but I guess I think it's more likely not to be something that will dissipate. I have in mind a complicated landscape of states that have different vacuum energies, metastable states that can undergo transitions from one to the other, and that the vacuum we see is one of those states. I think it's less likely that it would be something like a scalar field that was in the process of rolling down a hill in its potential energy diagram, just because that involves more parameters, and it seems to me that involves more special choices and is less likely.
Well, let's talk about likely and less.
I will go back to reiterating that I do think we're not very good at guessing these things, so that could be wrong.
And it's great. Let me point out again for people, the fact that we're not that good at guessing things is a strength of science, not a weakness, because it means we have to keep looking. Nature will tell us the answer. And that's why we have to keep doing experiments and observations, because it's the only way we're going to find the answer. It's not going to be a bunch of people sitting in a room without windows arguing at a blackboard. It's going to be some other way. But having said that, let's talk about your preferred. Let's talk about internal inflation, your preferred kind of models, where you think inflation is now, and where you think sort of the issues are, and what's the most attractive possibilities.
Okay, very good. Yeah, no, we should definitely talk about eternal inflation, because I have a strong interest in it, and a strong belief that that's probably the way the universe works.
And it seems very attractive as well. And of course, it'll get us back to the beginning too, but go on.
Right. Yes, it will. So to set the stage, eternal inflation refers to the fact that for most, if not maybe even all successful versions of inflation, when inflation ends, it ends because of random things that happen. So it doesn't end all at once throughout space uniformly. It ends in places and continues in other places. And in the places where it ends, it begins a Big Bang evolution, which leads to a local universe. I like to call them pocket universes.
Yeah.
And when inflation ends over here, a pocket universe forms here, and then a pocket universe forms there, and then there and there. And meanwhile, the whole background is exponentially expanding. So the number of pocket universes that is produced is ultimately infinite. And even the rate at which they're being produced grows exponentially. So we get not just one universe, but for free, we get an infinite number of universes. This is often coupled with the idea that the underlying laws of physics very likely allow different kinds of vacuum to exist. And this is certainly a feature of string theory, but if string theory is wrong, it could very well be a feature of some other fundamental theory. Right now, string theory is, I think, by far the best guess we have for a single theory that might describe the world. So that would mean that when these different pocket universes form, they can form in any one of the different possible vacua that the theory allow. And that could mean that the pockets could look very different from each other in these different kinds of vacua, because there'd be different kinds of ways the vacuum can bend and twist, different ways it can be excited. The low energy laws of physics would look completely different from one pocket to another, even though I am talking about a system where I'm imagining that the ultimate underlying laws of physics are the same everywhere. I don't really know how to talk about anything that would go beyond that. It's hard enough to understand one set of laws of physics. To speculate about other sets that might exist elsewhere is, as far as I'm concerned, not a useful exercise. So I'm only talking about a region of space that is governed by a single set of laws of physics, but nonetheless, different pockets can behave very differently. And that gives underpinning to these anthropic arguments that previously, for me, seemed somewhat crazy. But applying it in particular to the cosmological constant, which is one of the big problems in theoretical physics and cosmology, And this is the problem of why is the vacuum energy density so incredibly small by particle physics standards. Um, by what seems like a reasonable standard to compare with, the vacuum energy that we observe is about 10 to the minus 120th of what we might expect. Where I'll use the word, what we might expect is what we call the Planck scale.
Yeah, yeah.
And that doesn't have to be what everybody expects, but it's a reasonable number.
Even if it's 10 to the 60 times smaller, it's still 10 to the 60 times smaller than that.
That's right. Exactly. Exactly. Even if you don't want to go to the Planck scale, even if you just want to talk about the energy scales of the LHC, for example, you're still 60 orders of magnitude away from, that is, the observed value of the vacuum energy is still about 60 orders of magnitude smaller than what you would estimate. So it's a big mystery, but one of the possible resolutions, which I think is a very real possibility, is that with this huge infinity of pocket universes, each of which would have its own vacuum energy, some tiny fraction of them would have vacuum energies as small as what we observe. And then one wants to argue that those are the only places where life would form. It's certainly the case that if we had a pocket universe where the vacuum energy was at this Planck scale, the expected scale by some standards, if that vacuum energy were positive, the pocket universe would implode in 10 to the minus 43 seconds or something like that. And if it were negative of that magnitude, it would fly apart in 10 to the minus 43 seconds. So it's very easy to believe that life would never form in pocket universes that are typical, which have vacuum energies of the order of the Planck scale. So the argument goes that perhaps the reason why we observe such a tiny vacuum energy is just that life only forms in universes that have vacuum energies that small, and that explains the problem.
Well, let me step back and parse this a little bit. One of the things I do, and it'll be the rare case where I'm trying to make what you say more precise rather than the other way around.
Okay, go ahead.
Because we've debated this in a different context, but I think one would say it's fair to say that where life like ours would form. I mean, so the argument works even if you don't. I mean, there could be life in other. There could be living systems in universes that are very different than ours. So I mean, we can't imagine. And by the way, one should point out that the person who came up with this argument was Steve Weinberg again, having to do with the cosmological constant in 1987, before it was observed as well.
Right.
And the point is that
I'm not sure if he deserves credit for coming up with the idea, but he certainly is the first major physicist to support the idea.
Yeah, to support the idea. Well, yeah. I mean, in 1987, in his Reviews of Modern Physics, it's the first place I saw it written down anyway. But and the idea is really even simpler almost than said, is that you need as far as we know, you need galaxies to form us, because you need stars and they need planets for you and I to be here to talk. And in order to have galaxies form, you have to not be expanding too fast, because if the repulsive force is bigger than the sort of attractive force that causes matter to collapse, you wouldn't have any matter collapsing. And so to have a universe with galaxies and stars, it turns out the cosmological constant can't be much bigger than what it's seen to be. And lo and behold, it has that value. And that certainly lends credibility. But I think it's fair to say that it's important to point out that we don't know the locus of possible life. I mean, it could be that life could exist in universes with vastly different laws of physics. It just wouldn't be life like ours. And those life forms might be asking exactly the same question. Why does their universe seem so nicely tuned to their existence? And I think it's worth pointing out that what the multiverse that you're talking about does naturally is explain potentially why the energy of empty space is what it is in a universe that looks like the universe that allows us to live in. It doesn't say that there couldn't be other universes with life where people wouldn't be asking that question. And I think that's the reason I'm saying that's important, is because some people think this is an incredible fine-tuning problem, or that the multiverse is invented by people like you and me to just either get rid of God or to try and finesse this problem. And the point is, once again, it wasn't developed as something anyone wanted. I don't think you or I probably would have liked the idea of a multiverse when we were studying physics. We wanted there to be one universe that has to look like the way it does, and that there aren't other possibilities. We're sort of dragged kicking and screaming to realize that this is a likely possibility, first of all, and then secondly, that if it's a likely possibility, it happens to potentially be a natural explanation of something that's very weird, namely why the energy of empty space is what it is. So I think I want to just sort of once again stress that we're trying to explain why it is natural in a universe that looks like the universe we live in to have an energy of empty space that's absurdly small. The multiverse solves that problem.
Okay, I guess actually I do have a slightly different take from you.
I know.
Yeah.
We've
Okay.
debated this in the past, but go on. I want to hear it.
Right. I guess I have a stronger criterion for believing that the explanation is plausible. Is probably the right way to phrase it. I would say that if the life like us was really an important restriction, and that there was lots of other life that was not like us, that they outnumber us by a huge amount, that would make it not a satisfactory explanation. The way I would look at it is, I would say, if we are very unusual, say we had a spot on our left ears that identified us as being unusual types, and if you convince me that people who have spots on their left ears should live in a universe like us, but for every such person, there's a million who don't have spots on their left ears, who would see a completely different world. I would say that that's not a good explanation for the world that we see. Why do we happen to be the people who have spots on our left ears? So I would like, in order to accept this explanation, that it ends up predicting that essentially most, doesn't really have to be all, but most life in the very general sense would live in regions that have very low cosmological constants.
Okay, and I think
that's plausible also. And
yeah, absolutely, it is. It is plausible, and I think, and this is where we get to. I think it's important. This is where we get to the subtle questions that really are the kind of things that people debate now, and hope and may one day be resolved by observation or experiment. And we'll get to that. Is these sort of subtle questions of whether the problem with all of this, to be fair, is that when one is trying to calculate how likely or unlikely something is, you have to know about probabilities, and you have to know about the phase space of possibilities. And the reason that we can vastly differ in what we say is that we don't know the probabilities, we don't know the phase space. So this is all, and until we do, it's fair to say I think this has to remain sort of speculative.
Yes, I completely agree.
Yeah,
so it's perfectly okay for us to disagree, and neither of us should claim that we have good evidence that we're right.
Yeah, and we don't, and so it's an open question, but it is a fascinating fact that I think, once again, a corollary of inflation. I think I said some people use a different way of pronouncing that word, but I say corollary. But anyway, is an unexpected result is the fact that a multiverse is the generic prediction of inflation rather than the other way around. That it's really comes back to your original problem. Inflation doesn't end gracefully.
Yes.
And the point is, in the multiverse, it doesn't end gracefully. That there's universes being created all the time, and some of them may collapse or other. There's big bangs all the time, and it's going on eternally, and it never stops for the reason that you've kind of realized at the beginning that you couldn't solve what you wanted.
That's right. We've come back there.
And so the fact that inflation goes on eternally is a generic property, but it's not a negative. It turns out to be a positive, because one of the side benefits, besides predicting fluctuations, is that it gives a possible explanation of something that's really difficult to understand otherwise, namely why the energy of empty space is what it is. Now, let me point out for people who are going to say that, okay, well, this is all speculation. You guys aren't this is all science fiction. And this has been important to me because I've written about this a lot and thought about this a lot and predicted some things in advance. But this can be tested. And people say, how could you ever test the existence of other universes? And as you know, I've been thinking a lot from the early stages of COBE, and maybe you don't, I think you know, about observing what are called gravitational waves from inflation, which one could say, as we said earlier, inflation is an idea, and it comes from just the merging of quantum field theory and general relativity, and therefore it's an idea more than a model, and therefore there's lots of possibilities. And some people would say the negative feature of inflation is it can explain almost everything, no matter what it is. An inflationary model could probably explain it, and that's been pointed out as a negative by some people who like to criticize inflation. But one of the things that inflation does produce almost uniquely is a background of gravitational waves of a certain type, which could be detectable, and for a while we thought had been detected. For a brief moment of excitement in your life and mine, we thought had been discovered these certain modes in the Cosmo Microwave background that would look for gravitational waves, which are pretty well unique prediction of inflation. And so I would say that these ideas are testable, and tell me if you think I'm overstating it, that these ideas are testable because if we could measure gravitational waves from inflation, we could hone in on the kind of inflationary model that might exist, and that model would tell you if there was internal inflation. And if that model told you that, then it would be clear indirect evidence that multiverses existed, even though we'd never be able to detect them directly. And I would have said that that's not much difference than the indirect evidence that atoms existed well before you could ever see atoms. Am I overstating the case?
No, I think that's right. And I do sometimes make exactly that point, that we are narrowing down the possible physics of the field that drives inflation, the inflaton field. And we can hope to eventually narrow it down so much that we'll be able to tell whether the inflationary model that best fits the observed universe also predicts a multiverse.
Yeah.
And I think it's a very important principle, which I think is real, that you don't have to confirm every prediction of a theory to decide that the theory is right.
Yeah.
If you can confirm enough predictions and don't find any discrepancies, you could become convinced that the theory is right.
Yeah.
And that certainly is ultimately what's true about everything. I mean,
yeah.
Even Maxwell's equations predicts lots of things at huge scales that we've never measured and never will measure. But we believe that if we ever observed those scales, they would have been Maxwell's equations.
There's no reason to believe that it wouldn't be anything else. And right. The simplest argument is that and I think that's for me, what is fascinating is that turns what is metaphysics into physics, because a lot of people criticize multiverses, and the point is we may eventually, it's plausible, although not guaranteed, that we will be able to have measurements that tell us that there are other universes out there without ever knowing, without ever clearly ever being able to measure them directly. But empirically, because the theory, if it explains 50 things that are measured, and the 51st you can't measure, as you just say, well, it's highly likely to be there, and so we'd accept it, just the way we accepted atoms well before we could ever see them. And so that argument against inflation, I think, or against multiverses, is really misplaced, and I wanted to stress it. First of all, because they came out of the theory, they weren't put in, and secondly, we may be able to measure them. And the other, so measuring gravitational waves, which I've been pushing for since COBE, I think, is important for that. But also recently, I've been excited because, as you probably know, I argued with my colleague Frank Wilczek that if you could measure gravitational waves from inflation, you'd also prove that gravity is a quantum theory, because they wouldn't. Because if gravity wasn't quantum mechanical, then those inflation wouldn't produce gravitational waves. And I think that's really remarkable. I don't know if you're familiar with it, but I'm very excited.
Now that you mention, I did hear about it, and yes, I agree. I agree.
Because
I guess I assume gravity has to be quantum mechanical, so I don't worry about it much. But you're right; it's one of these fundamental questions.
And there are some people who think that and there are some people who think the solution to this problem of merging quantum mechanics and gravity is that quantum mechanics stops being true at some fundamental scale, including people maybe even Roger Penrose and others. Yes. So there are some reasonably good physicists who would argue that maybe you don't have to have both of them, and that's why I find the possibility of empirically measuring it to be so exciting. Because if you did, then it would just remove that whole possibility of philosophical and maybe physics speculation. Okay, in the last few minutes, let's go back to the beginning. because inflation generically predicts, as we say, that the universe is eternal, which means it continues going on once it starts, but it has to start. And I'm happy to say that you and I agree about many things, but you were the first person that I've ever heard say the ultimate free lunch, that inflation gives us a universe which is the ultimate free lunch. But it may even be more simple than that, that quantum mechanics can actually produce universes for free, because the total energy of our universe could, say, be zero. And as you know, that was the arguments I gave in my book, The Universe from Nothing. And inflation gives the motivation for that. But I think we are agreed that seems to be, both of us, the most likely possibility, that universes can, literally space and times, can pop into existence from nothing. And the ones that can survive are the ones that probably have zero total energy in one way or another, and end up looking like ours, right?
Yeah, no, I certainly think it is important that our universe is consistent with having zero total energy, with the negative energy of gravity canceling the positive energy of everything else. And I think we know that is a highly accurate statement, if not exactly true. And I think that does mean that our universe can arise from nothing. In terms of what the history of our universe actually is, if we followed it backwards, I now have actually two favorite alternatives, one of which is the one you just mentioned, creation from nothing through a quantum transition. I'm also now rather keen about an idea which I think is really originally Sean Carroll's, the idea of a two-headed arrow of time.
I've heard you mention that, and I'm suspicious about it, but okay.
Okay, so I'll describe it for you and our listeners. The idea, and we claim that this is a generic behavior for many kinds of mechanical systems, a crucial feature of the underlying mechanical system, and I'm now thinking of our universe as being one mechanical system, a crucial feature for this to be possible is that there has to be no upper limit to the entropy of the system. The system has to be capable of getting bigger and bigger with more and more entropy. And an eternally inflating universe certainly seems to meet that bill. It seems to be able to increase its entropy forever without any glitches. So we have in mind eternal inflation here, but we think of it really in terms of a simpler model. The idea is that if you start such a system in a more or less arbitrary state and follow it into the far future, one would expect the entropy to grow. If you start at most any state and follow it for a long time, the entropy grows. So here's our space-time diagram. We start here. Starting here makes it a kind of a logical beginning, but it won't really be a chronological beginning, because I'm going to talk about what happened before. Logically, we start at some arbitrary state here and follow it to the future, entropy grows. But if we follow it to the past, because the laws of physics are completely time symmetric and we just chose a random state, everything that we said about the future applies also to the past. Entropy grows to the past. So if you define the arrow of time as the direction that entropy is growing, it becomes a two-headed arrow of time. I don't know if I'm entirely on the screen here.
Yeah, you are.
With the arrow of time in the future pointing to the future, and the arrow of time in the past pointing to the past, and a finite region in the middle where the arrow of time might not be defined. That means that in almost all of space-time, really, space-time would be infinite and only a finite region where the arrow of time is ill-defined. So the arrow of time would be well-defined everywhere, almost everywhere, I guess is the way the mathematicians would describe it, everywhere except for a set of measure 0. And it gives a very natural explanation for the existence of an arrow of time. It seems to be almost unavoidable.
Yeah, well, I mean, people have tried to tie the arrow of time to the growth of entropy in good and bad ways. Stephen Hawking, as you know, tried to do it in a very bad way once, because he'd argue that somehow time would flip if the universe was contracting, and I think we all agree that's not true.
Right. Stephen did too eventually.
Yeah, so I guess I wanted to give you a chance to give an explication, if not an explanation, of that idea. But what it does do, and again, I think it's interesting because it does suggest, in a way that's not that different than maybe, at least in spirit, than Hartle-Hawking is that there doesn't have to be beginning of time. That while that there doesn't have to time doesn't have to have a beginning, even if the universe isn't eternal in that sense, in the traditional sense. When you go back to what you think is the beginning, it may not be a beginning.
Right. Time, the notion of time might change dramatically.
And that's one example of it. But I mean, all of those are, those are just, they're just speculations, because of course we don't have a theory of the beginning.
Yes, it's certainly fair.
And I think it's worthwhile. But it's important because it obviates one of those things, which, as you know, I've had the misfortune of having to debate at least one apologist who used a result of yours and our good friend Valenkin's, and which seemed to suggest that the universe had to have a beginning. But that was only if you that's true if you assume there's nothing new, no new physics, basically. And we all expect there to be new physics at some level. So it's fair to say that. Okay.
Yes.
But if we go back to this beginning, the last thing I want to talk about is to touch on because I did just, as you know, do a podcast with Roger Penrose, and he's been a longtime critic of inflation, and I've always thought for the wrong reasons myself, and I'm sure, and to be fair to him, you and I are, of the same view here, so we may be giving him short shrift. Some people, as I say, thought I gave him a kind of a hard time when I talked to him, but I think I was being fair in the sense that what we now know suggests that inflation is kind of like cancer in a way, in the sense that you can't get away from it in one way or another. And the hard part is getting it away from it, not having it happen. And therefore, to argue it somehow the world is fine-tuned, and he would go back to this question of entropy at the very early times. And I think you've listened to the argument I gave him, but I want to give it to you here, and then I'd like you to pick it apart, especially if I said it wrong, incorrectly. Is that there will inevitably, you might argue, as he might argue, that it's incredibly improbable to have a region, as you say, you solve the horizon problem because the original universe is very, very small, and therefore there's time for it to homogenize. There's time for, and he would say, well, but entropy arguments would suggest that it'd be very inhomogeneous, and that you wouldn't expect to find a region which would be uniform enough for inflation to happen. But my argument is that probability argument doesn't work, because the minute there is such a region, you're guaranteed that almost all of space in the long run has to be part of that region, because inflation is eternal. Is my argument wrong or right?
I think it's essentially right. There is a catch, which is that we don't really know how to talk in any rigorous way about fractions of space and space-time because of this measure problem, which we haven't mentioned yet. But maybe we should tell our listeners about the measure problem.
Okay, why don't you?
The problem is, this is a feature of eternal inflation that we don't completely understand. Some people argue that because we don't completely understand it, it must mean the whole theory is wrong. That's not the way I look at it.
Yeah.
I look at it as something that we don't yet understand.
Yeah. It's like I used to say that evidence of not understanding something is not evidence for God. It's just evidence that you don't understand stuff. Yeah,
that's right.
I think it's important.
That's right.
Okay.
It's fairly human to not understand something.
Yeah.
So I think we just need to accept that. So the problem is that because eternal inflation produces an infinite number of these pocket universes, trying to describe the statistics of them, what fraction of them are blue or have any property that you might invent, the number that are blue is infinite, the total number is infinite, the fraction that are blue is infinity divided by infinity, which is not mathematically well defined.
Well, it can be defined, but it gives you can find it many different ways. I think that's the way to say it.
Not uniquely defined. Maybe qualify that.
Yeah.
But yeah, not uniquely defined, probably is actually a much better way of saying it.
Yeah.
Because our goal is to find a way to define it by some kind of a regularization procedure. And we do have ways of defining probabilities in eternally inflating universes, ways that we've just made up, but which give sensible answers. It also turns out, by the way, that sensible sounding recipes can sometimes give very nonsensical answers when you think about it more carefully. That was one of the surprises in this business. We won't go into details there.
Yeah.
So it's a non-trivial issue to decide if a recipe gives sensible answers or not. And we do have recipes that give sensible answers. But what we still don't really have a clue about, as far as I know, is anything that really determines what the right answer should be.
Yeah.
And that's important. So there definitely is an important missing piece in this puzzle. And for that reason, I don't like to talk about what fraction of spaces are inflated and what fraction haven't, because it does depend on having an answer to this question.
Yeah, I guess so. But I guess my point was that once it happens, it's hard to stop. And then,
yeah, no, that's certainly true.
And it's hard to beat an exponential.
Yeah, no, all that is true. So I think at the intuitive level, what you said is definitely right. And at a more precise level, we certainly do have ways of defining probabilities, which we can think of as being part of our assumptions of the theory for now. Although in the end, I think we definitely want to have a way of deriving the procedure for calculating probabilities. But we do have ways that make everything fit together and everything plausible.
Well, I want to give you a chance to just sort of respond here clearly to this question of entropy, which I still, I think it's a non-issue. I kind of get a feeling like it's a non-issue, but it's a very big issue to Roger. And so why don't you, if you want, to take a few minutes to describe what you don't think, what your take on the problem is.
Yeah, sure. Okay, my take is that if whatever we assume happened before, if we could imagine starting with a nascent universe, and in my two-headed arrow of time picture, this would be a region near the neck where the arrow of time is not that well defined yet. As long as one can find in that region, I'm thinking this is a big region which has lots of little regions. As long as one can find in that region a little speck that has the right conditions to start inflation, and those are pretty generic. It just means that you have to have, in this model of scalar fields, we need to have, for example, and there is even other possibilities, but for example, we need a local maximum and a potential energy function in a region of space where the field happens to be sitting on the top of that maximum. As long as something like that happens somewhere in the region, and it has to have a certain minimum size, but that minimum size is very small, then the physics of inflation takes over and builds an entire universe from that. And the initial entropy is the entropy of a tiny speck. So I don't think there's any problem explaining why it's small compared to the entropy of the universe today. I think it's exactly what the theory predicts. And what the theory predicts in terms of entropy is, I think, exactly what everybody thinks happened. The region starts to exponentially expand. When it does that, the entropy density goes down to essentially zilch because of the huge expansion.
1 second. Come back here. Sorry, I'm telling my dog. Go on. Yes.
Okay.
Come back.
So during the exponential expansion, the total entropy, the entropy density in this region disappears to zilch because it just gets so incredibly diluted. And meanwhile, the space-time just naturally develops into a de Sitter space. That's really a theorem that if the energy momentum tensor is dominated by this vacuum-like energy, the energy associated with a field on top of a hill, for example, that leads to evolution of space, which is called de Sitter space, which is exactly what inflation uses. It becomes smooth because of the exponential expansion. And then at the end, locally, something happens like the scalar field starting to roll down the hill. That releases a huge amount of energy into the fields without exciting the metric, because the interactions with the metric are incredibly weak. Gravity is incredibly weak. And you're left with exactly the state that Penrose describes as incredibly implausible. A state with a high entropy density of the matter and on a smooth spatial background.
Yeah, no, I mean, his argument a priori is that, yes, why does matter have so much entropy? Is there so much stuff, but gravity doesn't? Namely, why is it so smooth? And that, if you ask the question that way abstractly, it sounds unusual. But then if you have a physical mechanism that makes it happen, it's not so unusual, I think. And this is a generic physical mechanism. In fact, the first thing I guess I learned from you, maybe, I don't remember, but when I first heard about inflation, is that it produces an incredible amount of entropy. One of the big problems of understanding is why we have a hot universe. Inflation produces, what it's great at is producing entropy. And it does. And so it's not too surprising. I mean, that's what it's built to do almost. That's really the reason it solves all the other problems in a way.
Yeah. In some ways, we should maybe say that the flatness problem can be rephrased as the problem of where did all the entropy come from? How did we develop so much entropy? And the way to make the connection is that the flatness of the universe really is described by how many particles you have over a region of a specified amount of curvature.
Exactly. And it's fair to say, just to make a nice bringing things together, that that very problem that, as I said, caused particle physicists to think about cosmology, the why do we live in a universe of matter and not antimatter, is also a question of why we live in a hot universe, which is really why there are between 1 billion and 10 billion photons for every particle of matter, which is another way of saying why is there so much entropy in the universe. So it all comes back down to that question in a sense. So that I think that's where where you and I would differ from Roger, is that phrasing the question abstractly makes it seem like there's a problem, but there's a natural mechanism to solve the problem. The other thing I want to argue about, because again, I think people love this idea of an eternal universe that gets expanding, that some of the future is the past, and it's a cycle, because it's a beautiful picture, and people have thought about it a lot over the years, many different versions of cyclic cosmologies, because it's so nice not to have that. But I think it's fair to say that as I tried to argue with Roger, and I tried to be fair about it in a way, is that inflation requires no physics. You don't have to know any fancy quantum gravity. You don't have to, it just have to know basic physics, and it's a mechanism that automatically happens. To do this other stuff, you have to assume all sorts of things we don't know, and try and explain away things that we explain away things instead of explaining things, I guess, is what I'm thinking about. And to some extent, also not necessarily yet make predictions. And so those are the reason I were going to fall in one camp versus another. I would fall in the inflationary camp. Now he has been here but he did have his time with me. But how do you view those same issues?
Let's see.
The fact that inflation is just known physics, and CCC requires physics. Well, it seems to me to require physics we don't even know about, and I don't know.
Nobody besides Roger even thinks about.
Yes.
No, I think that's an important point, and I completely agree. The underlying physics of inflation is just quantum field theory and general relativity, both of which are well-established parts of the toolkit of theoretical physicists and the knowledge of physicists of all types. And we don't really have to assume anything new about principles of physics. While Roger's cyclic cosmology, I think you made both points very clearly, requires this mass fading, which is just a new feature of physics that Roger would like to assert happens with no real basis. And then the disappearance of entropy at the end of the cycle, which I find somewhat flabbergasting, really. He makes this huge point of saying that we need to explain why the entropy is so low. And then he provides a theory where the explanation is, well, maybe it all disappears.
Yeah, I know. It's just basically solving the problem. It's saying, it's like that. I think I said it to him like that famous Sidney Harris cartoon where there's this little gap that says, then a miracle happens. I think you should be a little more specific there. And look, it's fair to say that when we have these debates, we're not being unfair to each other, because first of all, extraordinary claims require extraordinary evidence. And so it's important. It's a sign of respect, I think, not disrespect, that one would argue with someone like Roger, who's clearly made profoundly important developments in physics, to say, well, you have, but this one we have a problem with, and it's necessary to ask what the problems are. And I think and Roger came back to me afterwards and saying, these things, I hadn't really thought about that aspect of inflation, and we're going to work on that problem. So so I think it's part of the. I think right at the forefront, that's where we can have these arguments. And you and I have had debates about many things at the forefront, even though we fundamentally agree about the fundamental physics. And that's the great part about physics. And the greatest part is that it's not going to be decided by who's a better arguer. It's going to be decided by nature, if it ever gets decided at all. And that's what makes science worth continuing. And I'll just end. I want to ask you, what's the future? What do you think? Where do you think inflation, dark energy, cosmology, where do you see the greatest opportunities? And it's something, by the way, just to advertise, that we'll be talking about at greater length when you and I get to be together at a public event that was delayed, that was supposed to be 2 days ago, and it'll be delayed till November because of my mother's unfortunate demise. But anyway, so what's the future?
Okay. Well, I agree with, I think, Yogi Berra, who says the hardest thing to predict is the future.
Yeah.
It's, I don't know. I mean, certainly we will continue to make, I think, very significant strides in pinning down the details of the behavior of the universe. Searches for possibly finding the gravitational waves that you mentioned, which would be so crucial in helping us learn about the early universe. And coupled with more precise measurements from the cosmic microwave background, maybe we'll discover non-Gaussianities, which should be there at some small level in inflationary models. And exactly what they look like will tell us a lot about the details of the early universe that we don't know now. So I can anticipate a very significant amount of progress along those lines, especially with things like 21 centimeter tomography becoming a bigger thing. The idea is that with only looking at the cosmic microwave background, we're seeing essentially a sphere around us, but with other methods that are beginning to come online, we can see the whole volume. And that gives a lot more information, a lot more statistics, better ways of pinning things down. On the more hyper-theoretical side of thinking about things like eternal inflation, I feel that we've kind of gone as far as we can go in doing the kind of thinking that we've been thinking about, which is basically exploring recipes for things like how to define probabilities. I think we've already explored a large swath of recipes, and we have a good idea of what might be consistent with what we observe and what isn't, but there's still a large class that's consistent with what we observe. And we're still, as I said, pretty clueless about what the underlying principle might be that determines the right answer. On that score, I think the best hope for an answer materializing in the next decades is through a better theory of quantum gravity, through really understanding the quantum mechanics of space-time, which right now we really don't. Even people who have faith in string theory don't really know how to even address the relevant questions.
Yeah.
So there's certainly a lot that we don't know there, and hopefully it's a lot that we will actually learn. I think it's going to be slow, but over the next decades.
Well, I think thanks, and I think I also like to say probably what we'll learn is the things we don't even know we're asking the questions about, and that's with the new science progresses, and this field of cosmology has progressed with new tools. And you're saying topography, 21 centimeter lines, one gravitational waves is another, a whole new area, window on the universe, and generally each new window on the universe surprises us. So and so as a theorist, I continue to sort of look to experiment more than theory, I think. But nevertheless, it's nice to be guided by wonderful theorists and have them as colleagues. And it was a wonderful gift to the world that that December night, not just because you discovered something that I think it may be an amazing feature of the universe, and the fact that we can even talk with any seriousness, as I've written in the past, about a universe, when it's 10 to the minus 35 seconds after the Big Bang, or when the size of the universe is smaller than the size of a single atom. The fact we can talk about that with any kind of seriousness is an amazing thing. And the fact we can do it and come up with interesting predictions, we can thank you for. But it's also, I'm very happy that besides what it did for physics, what it did for you is very important, because knowing you as a colleague, it's been a gift to all of us that it got you a job and you could be there to teach the rest of us. And since the time I've known you for many, many years, as an honest and wonderful human being. So thank you very much.
Thank you for those kind words.
Okay, thanks again for your patience, and I hope it was fun for you. I think it'll
It
be
was. It was
a
definitely.
nice way for the audience. So thanks again. I hope you enjoyed today's conversation. This podcast is produced by the Origins Project Foundation, a non-profit organization whose goal is to enrich your perspective of your place in the cosmos by providing access to the people who are driving the future of society in the 21st century and to the ideas that are changing our understanding of ourselves and our world. To learn more, please visit originsprojectfoundation.org.